Hello, fellow Sapiens, and welcome to Sleepless Homo. This is your quiet corner of the internet where you can let your mind slow down. Whether you're preparing to drift into sleep, cooking a late meal, driving through the night, or working with headphones on. Here, storytelling is soft, science-led, and never rushed. If you happen to drift off in the middle of a chapter, don't worry. I always place timestamps in the description so you can return the next day and pick up the story exactly where you left it. Because this is a channel for full journeys from beginning to end, where every piece matters. If you appreciate this kind of a long-form science, calm, careful, and humble enough to admit we don't always have the answers, then please consider liking and subscribing. That small action helps this quiet style of education reach others who might be looking for the same pause and the same comfort in a loud world. I also love hearing how you use these stories. Do you listen before bed, while showering or studying, or maybe in another time and place entirely? Share it in the comments. It always helps me imagine the strange little ways this channel fits into your life. And as always, stay curious, stay calm. Now, let's begin tonight's story, the complete deep sea story, from marine snow to monsters. If the oceans cover more than 2/3 of our planet, why do we still know less about them than the surface of the moon? It is a strange contradiction. We live on a world defined by water, and yet the great oceans remain largely mysterious, as if they were set aside as Earth's final frontier. When astronauts first looked back at Earth from orbit in the 1960s, they saw not a green planet but a blue one, wrapped in oceans so vast that continents seemed like scattered fragments. The sea is not a feature of Earth. It is the dominant environment, and yet, for most of human history, we have only skimmed its surface. The scale itself is disorienting. More than 99% of all habitable space on our planet is found in the ocean. Every mountain, valley, and forest you can see from a plane window is only a narrow strip compared with the living volume beneath the waves. But of that enormous space, scientists estimate we have directly explored less than 1/10. We have better maps of the highlands of Mars than we do of the ocean floor. Whole mountain ranges lie hidden under salt water, only dimly sketched by sonar and satellite. Even in the 21st century, every deep-sea expedition risks stumbling upon something no one has ever seen. The world we take for granted is, in reality, still uncharted. The story of how we have tried to approach the sea is as much about human limitations as it is about discovery. For most of our species' history, we were confined to the shorelines, making cautious ventures out on rafts, dugouts, or canoes. By the 15th and 16th centuries, during the great age of European exploration, sailors began to extend their reach across the open oceans. These voyages changed human history, but they did not unlock the depths. Mariners stayed on the surface, clinging to their fragile ships while the world below remained invisible. A sounding line with a lead weight was about as far as exploration went. It could tell you the depth of coastal shallows, but nothing of the vast mid-ocean basins. To them, the sea was a dangerous highway, not a place to study. It was not until the 18th century that the ocean started to be examined systematically. Explorers like James Cook carried naturalists on board, tasked with cataloguing the creatures of the surface and shore. They noted birds, fish, corals, shells, and the play of currents. But again, what lived deeper down remained hidden. When naturalists dredged the seafloor with nets, most of what they hauled up came back broken or unrecognisable. Some even argued that life could not exist in the deep. The assumption was simple. Darkness, pressure, and cold meant lifelessness. It was easier to believe in monsters than in ecosystems. The great turning point came with the voyage of HMS Challenger in the 1870s. For nearly 4 years, the Challenger circled the globe, equipped not for conquest, but for science. Its crew lowered dredgers and trawls into depths no one had seriously sampled before, sometimes taking hours just to haul equipment back to the deck. They discovered thousands of new species, mapped the first outlines of mid-ocean ridges, and measured the great abyssal plains. The Challenger showed beyond doubt that the deep ocean was not barren. It was alive, structured, and unimaginably vast. Its findings filled 50 thick volumes of reports, and many biologists spent the rest of their careers just cataloguing what the expedition had pulled up. The Challenger did not complete the map of the oceans, but it shattered the illusion that nothing lived below. From that point onward, the ocean was no longer a void but a world. Still, the limits of technology meant progress remained slow. Even in the early 20th century, exploration relied on dredges, nets, and the occasional diver limited to a few dozen meters. But then in 1930, off the coast of Bermuda, two men in a steel ball called a bathysphere were lowered more than 600 meters into the dark. William Beebe, a naturalist, and Otis Barton, an engineer, had built the contraption themselves, a thick sphere with a tiny window and a cable linking them to the surface. They had no engine, no steering, only a slow winch lowering them down into the black. What they saw through that tiny window stunned them. Living creatures glowing with their own light, fish of bizarre shapes and sizes, forms no one had ever imagined. Beebe later tried to describe them in words, but often he had no vocabulary. The bathysphere cracked open a door and showed that the deep ocean was stranger than even myths had suggested. By the middle of the 20th century, technology had advanced further. Sonar, developed in wartime to track submarines, began to reveal outlines of the seafloor. What had once been guessed as flat plains turned out to be sculpted with trenches, ridges, and undersea volcanoes. Geologists realized the ocean floor itself was moving, spreading, and consuming itself in trenches, evidence that became the foundation of plate tectonics. The deep ocean was not just a biological frontier but also a geological one. It was the machine room of the planet, recycling crust, venting heat, and storing the carbon and oxygen balances that keep Earth habitable. And yet, even with submarines, submersibles, and satellites, we remain outsiders. When we do visit the deep sea, it is usually in short bursts, hours at most. The longest human stay in a submersible at depth is measured in days, not months. Machines can linger longer, but the ocean is corrosive, crushing, and restless. Technology fails quickly there. In a sense, our glimpses remain like quick flashes of lightning on a vast landscape, illuminating small corners while leaving most in darkness. The irony is that the ocean shapes everything we do. It governs the climate by absorbing heat and circulating it across the globe. It draws in carbon dioxide, buffering us from even faster warming. Its currents dictate where storms form, how fisheries thrive or collapse, and how coastlines shift. Without the sea, Earth would not be the planet we know. And yet our knowledge of its internal workings is patchy. We model currents on supercomputers but still struggle to predict how they will shift over decades. We can track hurricanes, but the underlying drivers of ocean heat remain elusive. For all our satellites, much of the ocean floor is still more poorly mapped than the surface of the Moon, which was charted in detail decades ago. This ignorance is not for lack of trying. Oceanography has become one of the most interdisciplinary sciences on Earth, blending physics, chemistry, biology, and geology. Instruments now ride the currents like drifting buoys, sending back signals by satellite. Deep-sea rovers crawl along the bottom, cameras strapped to their frames. Fibre optic cables stretch across ocean basins and sometimes double as seismographs, detecting tremors on the seafloor. Every year, new techniques extend our reach, and still, the unexplored remains larger than the explored. There is a humbling perspective in this. As scientists, we admit openly that we do not have all the answers, that what we know so far is only a fraction of what is. The deep ocean resists simple narratives. It is not a single environment but many, layered in darkness and pressure. Each depth holds its own rules. Each region holds its own history. To imagine that we have it all mapped would be like trying to summarize all of Earth's continents with a single sketch. It is this scale that makes the ocean not just a scientific subject but an existential one. If we live on a planet dominated by water, then we live on a planet we do not yet truly know. The human relationship with the sea has always been paradoxical. On one hand, we depend on it for food, trade, and climate regulation. On the other, we have feared it, mythologized it, and sometimes ignored it. Ancient mariners told stories of sea serpents and krakens, not just out of superstition, but as a way of giving shape to the unknown. Even today, when a new deep-sea creature is caught on film, the language of myth creeps back into headlines. Monsters, aliens, leviathans. It is easier to imagine the ocean as otherworldly than to accept that it is part of our own Earth. But myths reveal something honest. We are unsettled by the fact that most of the planet is hidden from us. In the 21st century, exploration of the deep continues with small victories. In 2005, Japanese scientists managed to film a living giant squid for the first time, nearly a kilometre beneath the surface. In 2012, a team sent a submersible to the Challenger Deep of the Mariana Trench, almost 11 kilometres down, the lowest point on Earth. Every time a new camera descends, it seems, something unexpected appears. A fish swimming deeper than biologists thought possible. A coral reef thriving where none should. A plastic bag drifting where no human has ever walked. Discovery and disappointment side by side. The ocean, then, is not just another environment waiting to be catalogued. It is the hidden bulk of our own world. To speak of space as the final frontier is to overlook the truth that our greatest frontier is here, beneath us, filling the basins of our planet. We cannot live on Earth without it, and yet we do not know it. That contradiction is what makes the deep sea so compelling. It is not just a realm of creatures and geology. It is a reminder that our knowledge is partial, provisional, always unfinished. So we begin this story not with answers, but with questions. If the sea holds most of Earth's living space, why is so much of it still invisible to us? If life thrives in conditions we once thought impossible, what else might exist beyond our reach? And if we depend so deeply on the ocean's hidden workings, what risks are we taking by not understanding them? These are not rhetorical puzzles. They are the open questions of science. And they are why we descend again and again into the dark water, hoping for another glimpse. When did we first dare to go below the surface? For as long as human beings have looked out at the ocean, it has been a place of distance and fear, a horizon crossed but not entered. The line between air and water seemed like a boundary that could not be passed for long. Fishermen and pearl divers went down with weights and lungfuls of air, but always briefly and always within sight of the light above. For centuries, our vision of the deep was limited to whatever floated up or washed ashore. The idea of truly descending into the sea, of witnessing what lay below with our own eyes, was beyond imagination. That began to change in the 19th century, when a series of slow, cautious steps began to transform the ocean from mystery into a subject of science. The mid-19th century was an age of measuring. Empires were mapping the land with ever greater precision, charting rivers, mountains and borders. But at sea, knowledge remained thin. Mariners knew the coasts, the shipping lanes, and the hazards of reefs, but the vast spaces in between were blank. The practical tool for exploring depth was still the sounding line, a rope weighted with lead, dropped until it struck bottom. It was a crude method. The line might drift with currents, and the weight could only sample the narrowest spot on the seafloor. The ocean remained uncharted, both biologically and geographically. The very notion that life might exist in the great dark depths was disputed. Some scholars argued that beyond a few hundred fathoms there could be nothing, for pressure and absence of light would make life impossible. The turning point came in the year 1872 with the launch of HMS Challenger, a refitted British warship sent not to fight, but to explore. For 4 years, Challenger circled the globe, from the icy waters of the Antarctic to the warm tropics. Its mission was simple and audacious, to measure the depth, chemistry and biology of the ocean in a systematic way. The ship was equipped with dredges, nets, thermometers, and bottles designed to sample water at depth. Sailors lowered long lengths of hemp rope weighted with lead to sound the seafloor. The deepest reading they recorded in the Mariana region of the Pacific reached more than 8,000 meters, staggering to a generation that had barely conceived such abysses. The scientific crew of Challenger collected thousands of samples of mud, water, and living organisms. They found, to the surprise of many, that life persisted at every depth they sampled. Strange starfish, brittle crinoids, and shrimp-like creatures emerged from nets hauled up after hours of labour. These were not monsters of folklore, but delicate and specialised animals that had made the deep their home. Equally important were the physical measurements. Thermometers revealed that below a certain depth, the water temperature stabilised at just a few degrees above freezing, uniform from ocean to ocean. Glass bottles equipped with ingenious valves captured water at various depths, revealing salinity levels that were remarkably consistent across the globe. The Challenger expedition produced a massive legacy, 50 volumes of data published over 2 decades, cataloguing nearly 5,000 new species and transforming our view of the sea. The idea that the deep was barren had to be abandoned. Instead, the ocean was revealed as structured and alive, with layers of temperature and chemistry shaping where organisms could thrive. Yet even with this achievement, direct human presence in the deep remained out of reach. Scientists could haul up samples, but no one had yet looked out into the darkness from within. That step took another half-century. In the early decades of the 20th century, interest in the sea as a place of direct exploration grew. Divers were pushing limits with primitive helmets and air pumps, but their range was measured in tens of meters. To go deeper would require something entirely new. The solution came from an unlikely partnership between a naturalist, William Beebe, and an engineer, Otis Barton. Beebe had made his name studying birds and ecosystems, but he was fascinated by the idea of seeing life in its natural environment rather than in nets or jars. Barton, younger and technically minded, designed a vessel that could make this possible. Their invention was the bathysphere, a steel sphere just large enough to fit 2 men crouched inside. The walls were thick enough to withstand the crushing pressures of the deep, with small quartz windows barely larger than a fist. Oxygen was supplied by cylinders, carbon dioxide was absorbed by canisters of soda lime, and communication to the surface ran along the same cable that lowered them down. It was a primitive and risky machine, but it represented humanity's first attempt to truly descend into the deep as observers rather than collectors. In 1930, off Bermuda, Beebe and Barton began their dives. At first, they went down just a few hundred meters, still within the twilight zone where traces of sunlight lingered. But each dive pushed deeper, and by 1934 they had descended to more than 900 meters, further than any human being had ever gone below the surface. Through the tiny windows, Beebe described creatures glowing with their own light, fish with luminous spots and transparent bodies. He saw shapes that defied classification, animals so fragile they could never have survived the nets. He compared some of them to lanterns, others to ribbons of living glass. Some of his descriptions remain controversial, since no specimens were collected, but what mattered was the revelation that the deep was not a void, but a world of light and strangeness. The bathysphere dives captured the public imagination. Newspapers followed each descent, publishing Beebe's accounts as if they were dispatches from another planet. To many readers, the idea of humans suspended inside a steel ball staring into the darkness at glowing creatures was as fantastic as any science fiction. Yet behind the spectacle was a serious step for science. For the first time, direct observation joined indirect sampling. Scientists could begin to ask not just what lived below, but how these creatures moved, glowed, and interacted. The deep ocean began to feel less like an abstract abyss, and more like a living environment. Alongside these dramatic descents, quieter but equally important progress was being made. Instruments like the Nansen bottle, developed in the late 19th century, allowed oceanographers to collect water from specific depths with remarkable precision. These bottles, lowered on long lines, could be triggered to close at the desired depth, trapping a sample that revealed temperature, salinity, and sometimes even dissolved gases. By the early 20th century, refinements in these instruments made it possible to construct detailed profiles of ocean layers. Scientists discovered thermoclines, the sharp boundaries where warm surface water gave way to cold deep water. They traced currents not by sight but by the chemistry of the water itself, linking polar origins to equatorial depths. These measurements laid the foundation for understanding the great circulation of the oceans, the slow conveyor belts of cold, dense water that sink in polar regions and creep along the abyssal plains for centuries before rising again. Though invisible, these currents regulate the planet's climate and carry nutrients to sustain life. The bathysphere dives may have captured the imagination, but the bottles and thermometers were quietly revealing the machinery of Earth's largest system. Taken together, the 19th century voyage of Challenger and the early 20th century bathysphere descents mark the first true chapter of undersea exploration. One was broad and systematic, dredging and sampling across the globe. The other was personal and immediate, a pair of humans staring into the dark. Both revealed that the ocean was not empty. It was layered, alive, and complex. They showed that to understand it, we would need both instruments and imagination, both measurement and vision. But for all this progress, the limitations remained stark. The Challenger had mapped only fragments of the seafloor, leaving vast areas untouched. The bathysphere had no mobility, only a cable lowering it like a weight. The ocean still resisted our presence. It was as if it allowed us only glimpses, flashes of understanding, while keeping most of its secrets hidden. And that raises the haunting question that still echoes today. If after centuries of effort and ingenuity, we have only barely begun to see the ocean as it is, how much remains beyond our reach? What forms of life, what processes of the earth itself continue unseen beneath the pressure and darkness? The first descents were only the beginning, a reminder that the greatest part of our own planet is still a frontier. How do we divide something so vast and invisible into zones we can study? When you look out across the surface of the ocean, the water seems seamless, an unbroken expanse stretching to the horizon. But the moment you begin to descend, whether in imagination or by measurement, it becomes clear that the sea is not uniform at all. It is structured, shaped by physics and light, by temperature and pressure. To make sense of a world that stretches from the sunlit shallows to trenches deeper than the height of Everest, scientists needed to create a framework, a way of dividing the ocean into layers of depth. These are not arbitrary names, but boundaries born from measurable change, lines drawn where sunlight fades, where temperatures stabilize, where pressure mounts beyond comprehension. They are the architecture of the deep. The uppermost layer is called the epipelagic zone, but it is often simply referred to as the sunlight zone. It extends from the surface down to roughly 200 meters, though the exact limit can shift with water clarity, seasons, and latitude. Here, light still penetrates strongly enough to power photosynthesis, the process by which plants and microscopic phytoplankton convert sunlight into chemical energy. This is the reason the sunlight zone contains almost all of the ocean's visible green and blue life, as well as the base of the marine food web. Temperatures in this upper layer are variable, shifting daily and seasonally, warmed by the sun and cooled by winds and currents. Pressure here is still familiar to us. Divers can visit parts of it with equipment, and submarines can glide through it without extraordinary reinforcement. If the ocean were a forest, this would be the canopy, bright and full of activity. Beneath the sunlight, however, lies the mesopelagic zone, more evocatively called the twilight zone. It stretches roughly from 200 meters down to about 1,000 meters. In this layer, sunlight dwindles rapidly, scattering into dim blues and greens before disappearing entirely. By 600 meters, the light is too weak to support photosynthesis. It is not total darkness yet, but it is a shadowed world where day and night blur. The temperature here drops sharply, often forming a thermocline, a boundary where warm surface waters give way to much colder deep waters. For the first time, pressure begins to mount to levels that challenge human presence, dozens of times greater than at the surface. Oxygen levels can also dip in this zone, forming what scientists call oxygen minimum layers, regions where respiration by organisms depletes oxygen faster than it can be replenished. Even without describing the life that adapts here, we can say that it is an environment defined by scarcity, less light, less oxygen, and a rapid drop in temperature. Below the twilight lies the bathypelagic zone, sometimes called the midnight zone, extending from 1,000 meters down to about 4,000 meters. Here, sunlight no longer penetrates at all. The ocean is in complete darkness, illuminated only by whatever light is generated from within. The water is near freezing, usually between 0 and 4 degrees Celsius, and it stays that way year-round. The temperature stability of the midnight zone is one of its defining features. Unlike the surface, which is stirred by seasons and storms, these depths are calm and unchanging. Pressure here reaches hundreds of times what we experience at sea level. It is an environment beyond ordinary human comprehension, yet it covers vast swathes of the planet. If one were to sink into it, one would notice the absence of sensory cues. No sunlight, no waves, no storms, just stillness and crushing weight. Still deeper lies the abyssal pelagic zone, from 4,000 meters down to 6,000 meters. Its very name comes from the Greek word for bottomless, and it is apt. The abyss is unimaginably vast, covering more than half of Earth's surface. The water is uniformly cold, uniformly dark, and under immense pressure, ranging from 400 to 600 atmospheres. Sedimentation here is slow but relentless, particles of organic matter falling from the upper ocean and accumulating over millennia to form thick layers of soft mud. It is a place of monotony when described in physical terms, unchanging, calm, and immense. Yet precisely because of its stability, it represents one of the largest habitats for life on Earth, even if that life is sparse and slow. The abyss is not chaotic but orderly, regulated by the physics of water density and pressure. And then, below the abyss, there is one final frontier, the Hadal Zone, named for Hades, the underworld of Greek mythology. It begins at 6,000 meters and extends to the deepest trenches, nearly 11,000 meters in some parts of the Pacific. The Hadal Zone is not continuous like the layers above, but exists only in isolated trenches and troughs carved into the seafloor. Conditions here are extreme, pressures exceeding 1,000 atmospheres, perpetual darkness, temperatures just above freezing. It is an environment so harsh that for decades many doubted life could persist there at all. Yet, as we have slowly begun to explore, we have found that even in these trenches, ecosystems endure. From a physical perspective, the Hadal Zone is remarkable because of its isolation. Each trench is a separate pocket, cut off from others by ridges and slopes. They are like islands turned upside down, inaccessible and unique. To think of the ocean as a whole is overwhelming, but to think of it as layers makes it comprehensible. Each zone is defined by a simple principle: the sunlight zone by the reach of photosynthesis, the twilight by the last trace of dim light, the midnight by its total darkness, the abyss by its immense stable expanse, and the Hadal by its extreme depths and isolation. Together they form a vertical geography, as real and structured as the continents and mountains on land. Scientists have mapped the Earth's surface in exquisite detail, but when it comes to the sea, this layering is the first step toward a mental map. Of course, these boundaries are not fixed lines, but gradients. The ocean is fluid in every sense, and the zones merge gradually rather than sharply. Light fades slowly, not in steps. Temperatures drop across wide spans, not at single thresholds. The definitions we use are conveniences, chosen because they allow us to compare observations across oceans and across studies. They are the scaffolding of marine science, a way of organizing a realm that otherwise defies order. And like all scientific frameworks, they are imperfect, revised as new data arrives. But without them, we would be left only with the vastness, unable to make meaningful distinctions. As much as this layering helps, it also highlights our ignorance. We can name the zones, describe their temperatures, pressures, and oxygen levels, and trace their boundaries, but we have explored only small fragments of each. Less than a tenth of the ocean floor has been mapped with high resolution. Only a handful of trenches have been visited directly. The vast majority of these zones remain out of reach, even in an age of satellites and robotics. To study them is to accept that we are glimpsing only edges and samples, not the whole, and so the haunting question lingers. When we divide the ocean into layers of darkness, are we simplifying it enough to understand, or are we blinding ourselves to complexities we cannot yet see? Does the structure we impose reflect the true architecture of the deep, or is it merely the best picture we can form until technology takes us further? Like maps of early continents, these layers may someday appear crude, replaced by subtler divisions based on currents, chemistry, or unseen ecological boundaries. For now, though, they are the clearest way we have to imagine the sea as more than a single unbroken void, a reminder that even in darkness there is order, and even in immensity there are patterns waiting to be known. What lives in the first 200 meters where light still reigns? This layer, the epipelagic zone, is the surface of the ocean as most of us imagine it. Sparkling waves, shifting blues and greens, and shoals of fish darting in the sun. But beneath the beauty lies a system of staggering importance, one that quietly sustains almost all other marine life and even shapes the very atmosphere we breathe. If the deep ocean is a realm of mysteries and shadows, The surface zone is where sunlight writes its influence most clearly, fueling the processes that make the sea and Earth itself habitable. The story begins with organisms so small they are invisible to the naked eye, phytoplankton. These drifting, single-celled organisms capture sunlight and carbon dioxide to make sugars through photosynthesis, releasing oxygen as a byproduct. Collectively, phytoplankton generate more than half of the oxygen in our atmosphere, a contribution far greater than that of all forests and terrestrial plants combined. Some estimates suggest that roughly 7 out of every 10 breaths you take originated here, in the microscopic green factories of the upper ocean. Their abundance fluctuates with seasons, currents, and nutrient availability, forming blooms that can stretch for hundreds of kilometers, visible from space as swirling green patches. These blooms are not just biological spectacles, they are the foundation of the marine food web, feeding everything from tiny zooplankton to whales. Larger plants also anchor this sunlit world. Kelp forests, formed by giant brown algae, create some of the most productive marine ecosystems. They grow along coastlines where cold, nutrient-rich waters rise from the deep, often in places like California, Chile, or parts of northern Europe. A single kelp stalk can stretch more than 30 meters upward, forming underwater canopies that sway in the current. Within these forests, sea otters hunt for urchins, fish weave between fronds, and countless invertebrates cling to the holdfasts that root kelp to the seafloor. For humans, kelp is not only ecological but practical. It has been harvested for food, fertilizer, and even as a source of alginate, a thickener used in foods and medicines. Equally rich are coral reefs, which flourish in clear, shallow waters where sunlight can penetrate to the seafloor. Corals are animals, though their rocky skeletons give them the appearance of stone. They thrive in symbiosis with photosynthetic algae called zooxanthellae, which live inside their tissues and provide energy. In return, corals build the calcium carbonate structures that form reefs, some of which have grown continuously for thousands of years. These reefs cover less than 1% of the ocean floor but host more than a quarter of all known marine species. The colours and forms that divers encounter, branching staghorns, brain corals, and vast fan corals, are evidence of the diversity made possible by sunlight, clear water, and intricate ecological partnerships. Fish are perhaps the most visible inhabitants of the sunlight zone. Schools of tuna, mackerel, sardines, and anchovies migrate through these waters, feeding on plankton or smaller fish, while themselves serving as prey for larger predators. The dynamics of these populations are tightly linked to productivity at the base of the food chain. When plankton bloom, small fish thrive and predators follow. When currents shift or pollution disrupts these cycles, the impacts ripple upward, altering entire food webs. It is no coincidence that human fisheries concentrate their efforts here, in the zones where sunlight drives abundance. More than 80% of global fish catches come from the epipelagic, often targeting species that school densely near the surface. But the influence of this zone extends far beyond ecology. Physically, the sunlight warms surface waters, creating layers of stratification that affect global climate. Warm upper waters resist mixing with colder layers below, trapping nutrients at the surface in some places while limiting them in others. Oceanographers track these variations with satellites, measuring surface temperatures that reflect processes from El Niño events in the Pacific to the annual monsoon cycles of the Indian Ocean. Changes in surface productivity can alter weather patterns, fisheries, and even carbon cycles, linking the shallow ocean directly to human economies and livelihoods. Yet for all its vibrancy, the sunlight zone is also fragile. Coral bleaching, driven by rising sea temperatures, expels the algae from coral tissues, leaving reefs pale and starved. Overfishing has depleted stocks of tuna and other predators, unravelling the delicate balance of food webs. Pollution from plastics, fertilizers, and oil spills enters primarily through this upper layer, where human contact with the ocean is most intense. Microplastics, invisible fragments from degraded waste, now mingle with plankton in nearly every corner of the sea, raising questions about how deeply our influence permeates. Some scientists warn that the productivity of the epipelagic is already in decline, with long-term consequences for the oxygen balance of the planet. One of the most remarkable aspects of this layer is how quickly it responds to change. A nutrient pulse from an upwelling current can spark a plankton bloom in days, turning clear water cloudy green. A hurricane can mix surface layers with deeper waters, redistributing oxygen and nutrients in a matter of hours. This dynamism makes the epipelagic both resilient and vulnerable. Resilient in its ability to regenerate productivity, but vulnerable because it reflects and amplifies disturbances. It is a mirror for the health of the planet itself. The scientific study of this layer is both old and new. Early sailors could see kelp beds and coral reefs directly, noting their extent long before modern instruments. Microscopes revealed plankton in the 17th century, astonishing observers with the idea that invisible organisms ruled the sea. Today, satellites and autonomous floats extend our vision, tracking chlorophyll concentrations and water chemistry across global scales. But even with such tools, there is much we do not understand. The diversity of phytoplankton alone, with thousands of species adapted to different niches, remains only partly catalogued. The complexity of reef ecosystems, where chemical signals and symbiotic relationships interlock, continues to surprise us. The epipelagic is often taken for granted because it is the part of the ocean we can see. Tourists snorkel above reefs, fishermen cast lines, and cargo ships traverse its surface, yet it is also the most critical layer for life as we know it. Without the oxygen production of plankton, the ecological engineering of corals, or the nutrient cycling of kelp, the entire planetary system would be impoverished. For all its accessibility, this sunlit surface remains a frontier of knowledge, demanding humility in the face of its complexity. And so we return to the question, what truly lives in the first 200 meters where light still reigns? We can answer with lists, plankton, kelp, corals, fish. But the deeper answer is that this zone is life's laboratory, where energy from the sun enters the ocean and sets the stage for everything below. It is where cycles of carbon, oxygen, and nutrients begin. It is where ecosystems flourish, but also where human pressures bite first and hardest. To understand the deeper ocean, with its shadows and mysteries, we must first reckon with this fragile foundation. And perhaps the haunting question is this: if we are already reshaping the sunlight zone, the brightest and most visible part of the sea, what chance do we have to preserve the layers of darkness that lie beneath? What happens when the sunlight fades to grey? Beyond 200 meters beneath the surface, the ocean enters a realm we call the twilight zone, or mesopelagic. Here, the bright beams of the epipelagic dim into an eerie half-light. Above, the world is still powered by photosynthesis and warmth, but here, light dwindles into scattered blue-green fragments. It is no longer enough for plants to grow, or for vision to guide every movement. It is instead just enough to give shape to shadows, and those shadows become the terrain upon which life must adapt. The twilight zone stretches from around 200 meters to roughly 1,000 meters below the surface. For comparison, if you lowered the Eiffel Tower into the sea, its tip would still not reach the halfway point of this band. This depth marks a threshold where light no longer rules, but darkness is not yet complete. It is a world of paradoxes, biologically rich yet invisible to casual eyes, globally important yet largely unexplored, alien in its strategies yet foundational to the survival of surface ecosystems. One of the defining features of this zone is the daily movement of life through it. Every evening, as darkness cloaks the ocean surface, billions of organisms ascend from the mesopelagic toward the epipelagic, feeding in the relative safety of night before retreating back down by morning. This phenomenon, known as diel vertical migration, has been called the largest daily movement of biomass on Earth. Tiny zooplankton rise first, followed by small fish, squid, and larger predators. At dawn, they sink again, vanishing into the twilight. The reasons are simple yet profound: to feed where plankton is abundant, but to avoid the predators that hunt in daylight. These migrations are not mere curiosities, but drivers of global carbon cycles. By consuming carbon-rich food near the surface and transporting waste downward, these animals help lock carbon into deeper waters, influencing the balance of Earth's climate. Because sunlight fades here, camouflage takes on new forms. In the epipelagic, transparency and reflective scales dominate, but in the mesopelagic, animals must cope with the faint downwelling light above them. Many species counter this problem through bioluminescence. generating their own light to blend in. Small organs called photophores dot their bodies, emitting soft glows that match the intensity of the light filtering from the surface. This adaptation, known as counter-illumination, helps conceal them from predators lurking below. What appears to us as a bizarre fireworks display is, to these creatures, a daily act of survival. Some species adjust their brightness in real time as they swim to different depths, a feat of biological engineering that humbles even the most advanced human technology. Bioluminescence is not used only for camouflage, it is also a language. Flashes of light can warn predators, lure prey, or signal potential mates. The exact meanings of these displays remain mysterious, for we cannot easily interpret them, but we know they are widespread, perhaps the most common form of communication on Earth by sheer volume of signals. In the twilight zone, silence reigns, but light speaks. One of the most spectacular examples of this world's inhabitants is the siphonophore. To human eyes, it appears as a single animal, but in truth it is a colony of specialized individuals, each genetically identical yet functioning as different organs. Some parts capture prey, others digest food, others provide buoyancy or reproduction. Linked together, the colony can stretch for tens of meters, longer than a blue whale. Moving silently through the half-lit waters, siphonophores trail tentacles that flash with bioluminescent sparks, both enticing prey and confusing predators. They embody a paradox of individuality and cooperation. Not one animal, but many, surviving as one. Fish too have adapted to this strange realm. Lanternfish, among the most abundant vertebrates on the planet, inhabit the mesopelagic in staggering numbers. Their photophores glow in patterns unique to each species, possibly even unique to each sex. During nightly migrations, they ascend toward the surface to feed, then descend again to the safety of depth. In their billions, lanternfish form the backbone of this zone's ecosystem, feeding larger predators and transferring energy downward. Their sheer biomass may rival that of all other fish combined, yet they remain almost invisible to us, their lives hidden in the ocean's grey band. The physics of the twilight zone reinforce its uniqueness. Temperatures drop rapidly here, a transition known as the thermocline, where warm surface waters give way to the colder deep. Currents and mixing are reduced, creating layers that separate nutrients from light. Oxygen levels can fall sharply in certain regions, forming oxygen minimum zones where life thins out or adapts with extraordinary efficiency. Animals in these areas often have slower metabolisms, reduced muscle, and specialized hemoglobins to survive with less oxygen. These physiological compromises illustrate how tightly evolution molds organisms to the invisible constraints of their world. Studying this zone is notoriously difficult. Nets brought up from depth crush delicate creatures, leaving only gelatinous smears. Submersibles and remotely operated vehicles offer glimpses, but the faintest light can disturb animals that evolved in near darkness. What little we know comes from rare captures, fragile observations, and the shadows caught on sonar. Yet the importance of this zone is immense. Global fisheries have begun eyeing lanternfish as potential resources, but scientists caution that disturbing this hidden engine of carbon transfer could have unforeseen consequences for climate and ecosystems. We know enough to recognize its importance, but not enough to predict what exploitation might bring. Historically, the Twilight Zone has played another role, that of inspiration and myth. For centuries, sailors imagined monsters lurking just beyond the visible. Even today, the half-lit waters stir our imaginations, not because of what we see, but because of what we cannot. Unlike the surface, which dazzles with obvious life, or the abyss, which terrifies with its emptiness, the Twilight Zone unsettles us precisely because it is neither. It is liminal, a place between worlds. The haunting question remains: what happens when sunlight fades to grey? We know that life persists, adapts and thrives, but we cannot yet claim to understand it fully. The mesopelagic is a frontier of both science and imagination, essential to planetary systems yet elusive to our instruments. Perhaps one day we will unravel the language of light, map the migrations in detail, and grasp the roles of these fragile creatures in global cycles. Until then, the Twilight Zone will remain the edge of familiarity, close enough to glimpse, but forever retreating into shadow. How does pressure shape the life that survives here? Past 1,000 meters, the ocean enters a realm where physics itself dictates who can endure and who cannot. For every 10 meters of depth, the weight of the water above adds another atmosphere of pressure. By the time you descend to 1,000 meters, the force is about 100 times greater than the pressure at the surface. Imagine the weight of a fully loaded truck pressing against every square inch of your skin, not once, but hundreds of times over. That is the invisible reality of the deep ocean, crushing, relentless, and inescapable. Yet life continues to exist here, and to thrive, though never on terms we would find familiar. Humans have always had a difficult relationship with this fact. At the surface, we are adapted to a single atmosphere of pressure. Even shallow dives of just a few dozen meters can strain our physiology. Divers must descend slowly to avoid bubbles forming in their blood, a phenomenon known as decompression sickness. The deepest freedivers in history without breathing apparatus have briefly reached depths approaching 250 meters, but their lungs are squeezed to a fraction of their size, and only extreme training makes survival possible. At 1,000 meters, no human body could endure such pressure without mechanical aid. Our tissues would not explode, as dramatic stories sometimes suggest, but our lungs would collapse, our eardrums would rupture, and our physiology would fail long before we could adapt. Yet other mammals manage this descent with apparent ease. The Cuvier's beaked whale, a medium-sized toothed whale, holds the record for the deepest mammalian dive ever recorded, reaching depths close to 3,000 meters and holding its breath for over 3 hours. How does it do this? Evolution has restructured its body in ways we still struggle to fully grasp. Instead of resisting the pressure, the whale allows it to collapse its lungs safely, forcing air into reinforced airways where it cannot form harmful bubbles. Its ribs are flexible, its chest cavity compressible. Blood is redirected away from non-essential organs to preserve oxygen for the brain and heart. Its muscles are loaded with myoglobin, a molecule that binds oxygen more efficiently than hemoglobin in blood, storing a reservoir that can be drawn upon during long dives. What would kill a human is routine for these whales, not because pressure is eliminated, but because their bodies yield to it in ways ours cannot. Technology provides another lens through which to appreciate these extremes. In the early 20th century, submarines designed for warfare rarely exceeded depths of a few hundred meters before the risk of implosion became fatal. The materials could not withstand the crushing forces. As metallurgy and engineering advanced, submarines capable of reaching 800 meters were built, though even these military giants skirted the edge of their structural limits. The hulls must be spherical or cylindrical to distribute pressure evenly, and even then the metal flexes slightly with every descent, groaning under forces invisible to the eye but catastrophic if miscalculated. Each extra 100 meters requires not a small adjustment, but an exponential leap in design strength and safety. The same physics governs deep-sea submersibles used in exploration. The bathysphere of William Beebe and Otis Barton in the 1930s was a steel sphere lowered by cable into the ocean. Its thick walls were designed to resist pressure down to 1,000 meters, and within that narrow space, 2 men peered through tiny windows at a realm no human had seen before. They were acutely aware that a flaw in the steel or a crack in the glass would mean instant death. Their lives balanced against the crushing patience of the deep. Later, the bathyscaphe Trieste in the 1960s pushed technology further, using a gasoline-filled float for buoyancy and a pressure sphere of thick steel to carry 2 men down into the Mariana Trench. The engineering solutions were all designed to resist or escape the problem of pressure, yet each remained a compromise. Marine life in these depths takes a different path. Rather than build shells or armor to withstand crushing forces, many organisms adapt by eliminating air-filled cavities altogether. Fish in the twilight and midnight zones often lack swim bladders, the gas-filled sacs that provide buoyancy at shallower depths. Instead, their bodies achieve neutral buoyancy through oils, fats, and specialized proteins. Gelatinous tissues cushion organs and reduce density differences that pressure would exploit. At 1,000 meters, it is not strength that ensures survival, but flexibility, softness, and biochemical ingenuity. Pressure also influences biochemistry at levels we are only beginning to understand. High pressures can destabilize proteins, the the molecular machines of life, altering their shapes and preventing them from functioning. To compensate, deep-sea organisms accumulate molecules known as piezolites, such as trimethylamine oxide, which helps stabilize proteins under extreme conditions. The cost of this adaptation is that tissues often smell or taste strongly to surface dwellers, a side effect of chemistry repurposed for survival. In essence, pressure not only shapes the physical form of animals, but also rewrites their chemistry. For humans and our technology, the struggle with pressure is always adversarial. We design stronger metals, thicker glass, and spherical capsules to resist the crushing force. For deep-sea life, the approach is opposite. Yield, adapt, and transform. It is a reminder that survival in extreme environments often depends not on defiance but on accommodation. And yet, despite these adaptations, the midnight zone is not without limits. Beyond certain depths, oxygen becomes scarce, temperatures hover near freezing, and even the most specialized biochemistry strains against physics. Few vertebrates descend regularly beyond 1,000 meters, and those that do are exceptions born of long evolutionary experiments. The silence and emptiness of these depths reflect the reality that life is possible, but only with compromise. Every exploration into these zones, whether by whale, human or machine, underscores a simple truth. Pressure defines the architecture of the deep. It dictates what bodies can look like, how chemistry must function, and how technology must be built. In this way, pressure is not simply a condition of the deep ocean. It is the sculptor of all its inhabitants, shaping them invisibly yet profoundly. So we return to the question, how does pressure shape the life that survives here? The answer, as far as we know, is through surrender. Whales collapse their lungs, fish abandon air bladders, submersibles surrender sleek shapes for awkward spheres. To go deeper is always to give something up. What else waits in the dark, adapted to pressures we have never endured, remains an open question. But one thing is certain. In the deep sea, pressure is not a background condition. It is the silent master of life, and perhaps the greatest obstacle standing between us and full knowledge of our planet. What does life become when the sun is gone? Beyond 1,000 meters, light ceases to penetrate. Not a faint shimmer, not a glow filtered through water, but absolute darkness. This is the bathypelagic zone, extending from roughly 1,000 to 4,000 meters, and it covers nearly 60% of the ocean's volume. It is a world where the familiar rhythms of day and night no longer apply, where the cycles of sunlight and seasons are erased, and where every organism must contend with the same stark equation. No light, no photosynthesis, and no easy food. Here, existence narrows to a matter of conserving energy, finding sustenance in scarcity, and surviving pressure that would crush steel. It is tempting to imagine this realm as barren, but it is not. It is simply alien. Life here follows strategies that surface dwellers can scarcely imagine. Where vision becomes useless, eyes diminish or disappear altogether. Where food is rare, metabolism slow, movements become minimal, and every gram of flesh is shaped by compromise. The shrimp that hover near hydrothermal oases, for example, abandon sight entirely. Instead of eyes, they carry light-sensitive organs on their backs, detecting the faint infrared glow of vents in the distance. To us they seem fragile, ghostly, almost spectral, yet they are perfectly tuned to the realities of a sunless ocean. Other creatures survive by becoming living contradictions. The vampire squid, despite its name, is neither particularly vampiric nor particularly predatory. It drifts slowly, conserving energy, cloaked in skin so thin it appears translucent, with arms linked by a web of tissue that resembles a cloak. Its name comes not from blood but from its deep crimson coloration, which in these depths is as close to invisibility as one can achieve, since red wavelengths vanish first in seawater. Instead of chasing prey, it gathers the faint detritus drifting down from the upper ocean, particles of dead plankton, fecal matter, and organic fragments that together are called marine snow. In a zone with no sunlight to fuel new energy, the vampire squid thrives by recycling the cast-offs of the surface. Its adaptations are not those of a killer but of a survivor. Large gills for extracting oxygen from thin water, low metabolic demands, and bioluminescent organs that flash in sudden bursts to confuse would-be predators before it retreats again into invisibility. Predators do exist here, but they too are creatures of efficiency. The viper fish, with a mouth packed full of fangs so long that they must fold inward when its jaws close, is a specialist of ambush. Its body is lean and muscular, yet it rarely wastes energy chasing prey. Instead, it drifts in darkness, motionless, until an unsuspecting animal is drawn toward the lure of its light-producing photophores. Then, in a flash, the jaws strike, the prey is impaled, and the long teeth ensure nothing can escape. Unlike the active predators of shallower seas, viperfish exist on patience and precision. Their survival depends not on frequent success, but on rare, decisive kills that provide energy for long intervals of waiting. Even the sharks that descend here reflect this pattern of conserving energy in extreme conditions. The frilled shark, often called a living fossil, patrols the midnight depths with an eel-like body and rows of needle-sharp teeth that curve backward, ensuring prey cannot slip away once caught. Its movement is slow, almost serpentine, and its strategy is not one of speed, but of sudden lunges when opportunity arises. It can go long stretches without feeding, its metabolism adapted to famine. In an environment where calories are scarce, such efficiency is a matter of life and death. Bioluminescence becomes the universal language of this realm. Without sunlight, creatures invent their own light. Some use it to lure prey, some to signal mates, some to startle predators. But even these displays are restrained, fleeting bursts designed not to waste energy. Every flash is a gamble between attracting what one hopes for and attracting what one fears. The darkness ensures that such light can carry across surprising distances, turning each glow into a risk as well as a tool. We know from submersible observations that the midnight realm is not empty. It is alive with drifting organisms, yet their abundance is nowhere near that of the surface layers. Instead, each species has stretched its physiology to its limits in order to persist here. Muscles are weaker, bones thinner or absent, and bodies often gelatinous. To our eyes, these animals seem fragile, but in truth they are specialists. Their fragility is an illusion born of comparison to our world. In their world, they are precisely what is required. The most striking feature of the midnight realm is not the strange appearance of its creatures, but the consistency of its environment. Temperatures hover just above freezing, currents are weak, and storms from the surface never reach these depths. For animals here, change is minimal. There is no dawn or dusk, no seasonal variation, only eternal darkness. Life here is not a story of adapting to constant shifts, but of fine-tuning to a near-constant void. Reproduction slows to match this stillness, with many species growing and breeding at glacial paces compared to their shallow-water relatives. Energy that might otherwise go into rapid growth is instead invested in endurance. Our knowledge of these animals comes largely from brief glimpses. Submersibles can descend for hours, but the cost and danger limit how often this is attempted. Many of the species we know from the midnight realm have been hauled up accidentally in trawls, their bodies distorted by pressure changes. Some, like the vampire squid, have been observed alive in aquaria, but they rarely survive long outside their environment. What we see are fragments of a world we cannot truly inhabit. And so, when we ask what life becomes when the sun is gone, the answer is both simple and profound. Life becomes slower, darker, more patient. It shifts from abundance to scarcity, from speed to endurance, from sight to bioluminescence. It survives not by defying the environment, but by embodying it, becoming creatures that seem strange only to us. But the haunting question remains, how much of this world have we yet to see? For every vampire squid or viperfish we know, how many others drift in the black water, unseen and unrecorded, living out entire lifetimes in a darkness we have only brushed against? The midnight realm reminds us that Earth's greatest wilderness is not on land but beneath the waves, and that much of it remains beyond the reach of our eyes. What if survival meant moving as little as possible? At depths between nearly 4,000 metres and 6,000 metres, we arrive at the abyssal zone, a place so stable and so uniform that oceanographers often describe it as the calmest environment on the planet. It is a world without sunlight, without weather, without seasons. Temperatures hover just above freezing year-round. Currents are weak. Storms from the surface never penetrate this far, and the sediment that carpets the bottom builds slowly, millimetre by millimetre, over unimaginable spans of time. The abyssal plain is vast, covering more than half of the Earth's surface, yet it is one of the least explored landscapes we know. This plain is not flat in the way a table is flat, but in the sense of geological quiet. Mountains and ridges do exist, but they rise from expanses so broad that they appear endless. Imagine walking across a desert where the horizon never changes. Only here the ground is composed of fine mud, enriched with organic particles that have drifted downward for weeks or months before settling. Some of this material is the so-called marine snow, though here it no longer looks like snow but like dust compacted into ooze. Much of the seafloor at these depths is blanketed by this ooze, sometimes kilometres thick, a record of millions of years of slow accumulation. Each layer contains microfossils of plankton and fragments of shells, a quiet geological diary of Earth's climate and ocean chemistry, written grain by grain. Because life in the abyssal zone depends almost entirely on this thin rain of organic matter, it moves slowly, eats slowly, and grows slowly. The scarcity of food imposes a kind of discipline on every living thing. Creatures here cannot afford to chase prey constantly, nor can they waste energy on displays. Instead, they adopt strategies of patience, ambush, or scavenging. Many animals live close to or on the bottom itself, feeding on detritus in the mud, or waiting in stillness for something edible to drift within reach. Their bodies tend to be gelatinous or weakly muscled, since powerful muscles are not required when both prey and predator move with the pace of a drifting shadow. One of the most endearing inhabitants of these depths is the Dumbo octopus. Named for the rounded fins on its mantle that resemble the ears of a cartoon elephant, this octopus seems almost whimsical as it flaps gently through the water. Unlike its shallow water relatives, the Dumbo octopus does not rely on ink for defence. The darkness here makes ink pointless. Instead, it uses its fins to glide slowly, conserving energy while probing the sediments for worms or crustaceans. Its soft body is perfectly suited to a world of constant high pressure, and its reproductive strategy is equally unhurried. Females carry eggs at multiple stages of development, releasing them gradually whenever conditions allow, rather than all at once. In an environment where encounters with mates are rare and unpredictable, this approach increases the odds that at least some offspring will survive. Fish too adopt the slow-motion lifestyle. Grenadiers, also known as rat-tails, are among the most common abyssal fishes. Their bodies taper into long, thin tails, and they spend much of their time hovering just above the mud, sweeping for invertebrates or scavenging carcasses that have fallen from above. They are not fast hunters, but opportunists, built for endurance rather than speed. Their large heads and sensory organs suggest that detecting faint vibrations and chemical traces is more important here than eyesight. Like so many abyssal species, grenadiers grow slowly and may live for decades, some estimates suggesting lifespans of 50 years or more. Sediments themselves are a part of the story. At depths shallower than 4,000 metres in warmer regions, the seafloor is often dominated by calcareous ooze, the remains of plankton with calcium carbonate shells. But below that depth, calcium carbonate dissolves under pressure, so the sediments shift to siliceous ooze and clay. Radiolarians and diatoms, microscopic plankton with silica skeletons, become the dominant contributors. The clays may carry dust blown from continents thousands of kilometres away, mingling with the microfossils in layers that accumulate at a rate of only a few centimetres every 1,000 years. If the seafloor of the abyss seems monotonous, it is only because its changes are written in the slow language of geology, not the swift events of human life. Scattered across these plains are something stranger, manganese nodules. These are potato-sized lumps of metals, rich in manganese, cobalt, nickel and copper, which grow layer by layer over millions of years around a nucleus such as a small rock or fragment of shell. They are of immense interest to mining companies because they represent concentrated sources of strategic metals, but their origin is still not fully understood. They form so slowly, millimetres per million years, that they are essentially non-renewable on human timescales. For the creatures of the abyss, they are simply another part of the landscape, providing hard surfaces where sponges and other sessile organisms can anchor in an otherwise muddy world. The calmness of the abyss does not mean it is lifeless. On the contrary, there is a quiet diversity here, though in far lower densities than in shallower zones. Sea cucumbers crawl slowly across the bottom, ingesting sediment and extracting organic matter from it. Some of these, like the transparent sea pig, extend delicate legs to walk across the mud, raising their bodies just enough to let currents deliver particles to them. Crustaceans scavenge in small numbers, while sessile animals grow on the occasional hard substrate. Many abyssal animals have long stalks or legs that lift their bodies above the sediment, rising into water layers that contain slightly more oxygen. Vision is minimal, pigmentation rare, and metabolism slow to the bare minimum required for survival. One of the great lessons of the abyssal zone is that time itself seems to move differently here. With no seasons to dictate reproduction, no sunlight to set daily rhythms, and food arriving sporadically from far above, many species abandon the schedules we take for granted. They reproduce slowly, grow slowly, and in some cases live astonishingly long lives. For example, certain deep-sea corals anchored on isolated mounds have been dated to thousands of years old, making them some of the oldest known animals on Earth. Fish and invertebrates likewise extend their lifespans, trading rapid growth for longevity. In the abyss, survival belongs not to the fastest but to the most patient. Our exploration of these depths has been limited. The abyssal plain is so immense that even after a century of oceanography, most of it remains unmapped at high resolution. The Challenger expedition of the 19th century sampled sediments with dredges, and in the 20th century, piston cores revealed climate history locked in the ooze. Today, robotic vehicles and submersibles occasionally visit, capturing images of Dumbo octopuses drifting like ghosts or grenadiers hovering above the mud. Yet what we have seen is a fraction of what exists. The abyss hides in plain sight, too remote for casual observation, too vast for systematic survey. What is perhaps most striking is how uniform the environment is across such immense distances. While the surface of the Earth brims with deserts, mountains, forests, and rivers, the abyssal plain extends for thousands of kilometers with little variation. Its calmness is deceptive, however. Beneath the mud, the tectonic plates still move, and at the edges of the abyss rift valleys and ridges mark zones of geological activity. But in the central plains, change is almost invisible on human timescales. If the surface world is noisy and restless, the abyssal world is hushed and enduring. So, what does survival mean here? It means moving as little as possible, conserving every calorie, waiting longer than seems imaginable for the next opportunity. It means evolving bodies that are soft, translucent, and efficient rather than muscular and swift. It means making a life not in abundance but in scarcity, finding continuity and stillness. And the haunting question that lingers is this: if more than half of our planet's surface is covered by abyssal plains, what lives out there that we have not yet glimpsed? What slow-motion dramas are unfolding in silence and darkness beyond the range of our eyes and instruments? The abyss is not empty, it is simply patient. And until we explore it fully, its secrets remain suspended in time, waiting for discovery. How deep can life go? That is the haunting question that guides us into the Hadal Zone, a realm beginning at about 6,000 meters and extending to nearly 11,000 meters at the very bottom of the ocean. The name itself comes from Hades, the Greek underworld, and it feels appropriate. This is not a uniform plain like the abyssal zone above it, but a fractured and scarred landscape of trenches, narrow valleys gouged into the Earth's crust, where tectonic plates collide and one slides beneath another. These are the deepest scars on our planet, and they create an environment unlike any other on Earth. The most famous of these trenches is the Mariana Trench in the Western Pacific. At its deepest known point, called Challenger Deep, the seafloor lies nearly 11 kilometers beneath the waves, deeper than the height of Mount Everest is tall. Here, pressure reaches more than 1,000 atmospheres, which is the equivalent of having 50 jumbo jets balanced on top of a single human body. The temperatures hover near freezing, though the water does not freeze because of the immense pressure. There is no light. And yet, against all odds, life persists. Exploration of these trenches has been slow and rare. The first attempt to reach Challenger Deep came in the year 1960, when Swiss oceanographer Jacques Picard and US Navy Lieutenant Don Walsh descended in a bathyscaphe called Trieste. The vehicle was essentially a floating tank of gasoline for buoyancy attached to a heavy steel sphere designed to withstand the pressure. The descent took nearly 5 hours, and the two men reported that at the bottom they saw what looked like flatfish, or some kind of benthic animal stirring on the seafloor. Their observation was later debated, since fish had not been expected to survive such extremes, but their presence down there changed the way scientists thought about life in the deepest trenches. Since then, very few people have returned. In the year 2012, filmmaker James Cameron piloted a one-person submersible called the Deep Sea Challenger to the same location, spending several hours on the bottom and collecting samples and images. Unmanned landers and remotely operated vehicles have since ventured into these depths more frequently, revealing a community of organisms adapted to conditions that seem nearly impossible. Among the most remarkable of these are Hadal snailfish. They look fragile and almost translucent, with soft bodies lacking scales, yet they are perfectly adapted to withstand crushing pressures. Their tissues contain high concentrations of small, organic molecules called piezolites, which help stabilize proteins and membranes under high pressure. These fish feed on amphipods, small crustaceans that themselves thrive in the trenches. Amphipods are abundant, scuttling across the seafloor and scavenging whatever organic material reaches the bottom. Some of them have been found with stomachs full of plastic debris, a reminder that even the deepest places are not beyond human reach. The amphipods are perhaps the most iconic trench dwellers, capable of withstanding pressures that would instantly crush most life. They have adapted by having flexible exoskeletons reinforced with unusual minerals, and by adjusting their biochemistry so that enzymes still function in conditions that would normally destroy them. The abundance of amphipods provides the base of the food web for snailfish and other predators. What surprises many scientists is not just that these animals survive, but that they appear to thrive, filling ecological niches in numbers large enough to sustain predators. Trenches are geologically active, with steep walls and frequent landslides triggered by earthquakes. These disturbances send pulses of sediment down the slopes, redistributing nutrients and reshaping the bottom. Because the trenches are so isolated and extreme, they tend to harbour distinct communities. Populations in one trench may differ significantly from those in another, even if the two trenches are relatively close in distance. This isolation makes each trench a kind of island, a unique laboratory of evolution. Another discovery in recent decades is that microbial life is abundant even in the deepest trenches. Bacteria and archaea thrive in sediments and water columns, metabolizing compounds that would be useless to us. Some specialize in breaking down organic matter under high pressure. Others oxidize chemicals released from rocks, drawing energy from the very crust of the earth. These microbes form the invisible foundation of Hadal ecosystems, sustaining amphipods and other scavengers. Human technology has had to advance dramatically to study these environments. Standard submersibles cannot withstand the pressure of the Hadal zone. Engineers use titanium spheres, synthetic flotation foams, and specially designed cameras to survive the descent. Each expedition is a logistical feat, and each glimpse into the trenches feels like peering into an alien world. The data are still sparse, but they suggest that life not only exists, but has adapted in unique ways that challenge our understanding of biology. What is perhaps most humbling is that the trenches may still hide organisms unlike anything we've seen before. Every time new equipment is deployed, new species are recorded, whether small invertebrates, microbes, or variations of snailfish. Because so few expeditions have been made, and each one covers only a tiny patch of seafloor, it is likely that the majority of Hadal biodiversity remains undiscovered. The trenches are also sites of chemical and geological interest. Sediments in these valleys act as repositories for organic carbon, trapping material that sinks from above. This carbon may remain buried for millions of years, influencing the global carbon cycle and climate. Studying these processes is difficult but crucial for understanding how Earth regulates itself over geological time. It is worth remembering that these trenches are not isolated curiosities but integral parts of the planet's tectonic system. They mark zones of subduction, where oceanic plates are forced beneath continental or other oceanic plates, recycling crust back into the mantle. They are therefore tied to earthquakes, volcanoes, and mountain building at the surface. To study the trenches is not only to study biology in extreme conditions, but to understand the deep machinery of the Earth itself. And yet, despite this scientific importance, we have mapped the trenches only in outline. Much of their detail is still unknown. Satellite altimetry provides a rough image of their shape, but only ship-based sonar can reveal them in true resolution, and so far only a fraction has been covered. When we say we know more about the surface of Mars than about the floor of our own ocean, it is especially true for these Hadal regions. How deep can life go? So far, we know it can reach the bottom of Challenger Deep, nearly 11,000 metres down. Amphipods scurry there, microbes flourish, and snailfish glide slowly in near-total darkness. But the haunting question is whether this is the absolute limit. Could there be organisms living within the sediments even deeper, perhaps kilometres below the seafloor itself, where rock pores still hold water? Some geologists suspect that microbial life extends into the deep crust, making the biosphere larger than we ever imagined. If that is the case, then the true answer is not just that life can go deep. It may be that life never truly ends, only changes form with the conditions. For now, we remain humbled by what little we have seen. The trenches remind us that the Earth is still largely unexplored, its greatest depths holding secrets that resist easy discovery. They are the planet's underworld, where pressure and silence rule, where light has never reached, and where living things continue to surprise us. What feeds life in the dark when photosynthesis is gone? That is the question that frames nearly every mystery of the deep sea. Sunlight disappears within the first 200 metres, yet living creatures are found all the way down to trenches more than 10,000 metres below. The energy that sustains them comes in a form that is both fragile and persistent. A slow rain of tiny particles drifting downward through the water column. Scientists call it marine snow, and without it the deep ocean would be an almost sterile desert. The comparison to snowfall is not only poetic but surprisingly accurate. In the upper layers of the ocean, plankton bloom and die. Small animals excrete waste. Larger animals shed fragments of skin, mucus and eggs, and dust and soot from the atmosphere settle into the water. These diverse materials clump together into irregular flakes that sink slowly, sometimes taking weeks to fall from the surface to the bottom. To an observer floating in the water column, the scene is reminiscent of a snowstorm in slow motion, with white and brownish specks drifting endlessly downward. At first glance, the flakes seem too insubstantial to matter. Each particle is fragile and can be disrupted by turbulence or consumed by animals in the mid-water zones. Yet taken together, marine snow represents one of the most important ecological processes on Earth. It is the mechanism by which the carbon fixed by photosynthesis near the surface is exported to the deep, supporting entire ecosystems in regions where sunlight never penetrates. Without this downward transfer, the majority of the planet's biosphere would be left unfed. The composition of marine snow is diverse. Some flakes are built around the empty shells of diatoms or coccolithophores, phytoplankton that form intricate skeletons of silica or calcium carbonate. Others are aggregates of fecal pellets, tiny cylindrical packages produced by zooplankton and small fish that feed near the surface and then excrete as they migrate downward. Still others incorporate dust carried by winds from deserts, soot from fires, or microscopic bits of plastic from human activity. Whatever their source, these materials stick together through mucus secreted by phytoplankton or bacteria, creating flakes that grow larger as they fall and collide with one another. Some reach several centimetres in diameter, drifting down like oversized snowflakes in a winter storm. The sinking rate of marine snow varies depending on density and size. Some particles descend only a few metres per day, while heavier pellets can fall hundreds of metres in the same time. Along the way, they are intercepted by a variety of organisms in the twilight and midnight zones. Gelatinous zooplankton like salps and pyrosomes filter them from the water. Small crustaceans graze directly on the flakes. Even fish adapted to the midwater darkness will seize clumps of falling debris. Much of the snow is therefore consumed long before it reaches the seafloor, and what remains is a fraction of the original production at the surface. But even this fraction is enough to sustain life in the abyss. When marine snow finally does reach the ocean floor, it accumulates into a fine blanket of ooze. Over millions of years, this ooze can build to depths of several metres, covering roughly 3/4 of the seafloor. Its composition changes with depth and latitude. In regions shallower than about 4,000 metres, the ooze is often calcareous, rich in the remains of foraminifera and coccolithophores. In deeper waters, calcium carbonate dissolves before it can settle, and so the sediments are dominated by siliceous remains of diatoms and radiolarians mixed with clays carried by currents. The result is a soft, uniform mud that records not only the biological productivity of the surface, but also the climatic and atmospheric conditions of past ages. Scientists use cores of this deep-sea ooze to reconstruct Earth's history. Tiny fossils preserved in the sediments reveal changes in ocean temperature, chemistry, and circulation over hundreds of thousands of years. Layers of volcanic ash mark eruptions long forgotten on land. Even pollen grains and soot particles carried across continents can be found embedded in the ooze, silent witnesses to environmental shifts. Thus, marine snow is not only the sustenance of deep life, but also the planet's memory, a slow archive settling grain by grain into the abyss. From an ecological perspective, the flow of marine snow is essential to what is sometimes called the biological pump, the process that moves carbon from the atmosphere into long-term storage in the deep ocean. Phytoplankton absorb carbon dioxide during photosynthesis, incorporating it into organic matter. When that matter sinks as marine snow and is eventually buried in sediments, the carbon is effectively removed from circulation for centuries or millennia. This process regulates the global climate, and its efficiency helps explain why atmospheric carbon dioxide levels have remained relatively stable for much of human history. Yet the efficiency of the pump is limited. Most marine snow never reaches the bottom. It is recycled in the upper kilometre of the ocean, where bacteria and zooplankton consume and respire it, returning carbon to the water and eventually the atmosphere. Only a small percentage of the original production, sometimes less than 5%, descends into the abyss. This fraction, however, is enough to support specialised communities of scavengers and benthic organisms. Life in the abyss is adapted to this meagre supply. Animals grow slowly, reproduce infrequently, and often live long lives. Many have developed strategies to maximise the intake of marine snow. Some extend delicate, fan-like appendages into the water to capture drifting particles. Others burrow into the ooze to extract nutrients from the sediments. The rain of marine snow is irregular, and so survival depends on patience and efficiency rather than speed. Even microbes take advantage of this continuous fall. Bacteria colonize the particles, breaking down complex organic molecules into simpler forms that can be absorbed by other organisms. In this way, each flake becomes a miniature ecosystem in itself, hosting a succession of microbial communities as it sinks through the water column. These microbes play a crucial role in determining how much of the snow reaches the deep, since their activity accelerates decomposition. To study marine snow is not easy. Its particles are fragile, and nets or bottles tend to destroy them. Scientists have developed special traps that can collect sinking material without disrupting it, usually by funneling it into slowly rotating containers that preserve the temporal sequence of deposition. These sediment traps have revealed that the flux of marine snow varies with the seasons, increasing during surface blooms in spring and declining in winter months. In polar regions, the pulses are especially strong, as plankton blooms in brief summers release a torrent of organic matter that sinks rapidly to the depths. In recent years, attention has turned to how human activity affects this delicate balance. Microscopic plastic particles, derived from degraded waste, are now common in marine snow. They act as artificial nuclei around which organic material can aggregate. While they do help form larger flakes, the plastics themselves do not degrade, and so they accumulate in sediments, altering the chemical environment. Likewise, soot from fossil fuel combustion and dust from expanding deserts contribute increasingly to the mix. These additions remind us that even the remotest seafloor is not beyond the reach of surface activities. The image of snow drifting through eternal darkness is both beautiful and unsettling. It shows how interconnected the surface and the depths truly are. The death of a plankton cell in sunlit water may eventually feed an amphipod in the Hadal Trench. A fish that grazes near the surface may excrete pellets that settle into the abyss, nourishing microbes that in turn sustain higher organisms. The link is unbroken, a chain of transfer that allows life to exist where it otherwise could not. And yet the process is precarious. If surface productivity changes, Through climate shifts, pollution, or overfishing, the flux of marine snow can diminish, leaving the deep communities starved. Because the inhabitants of the abyss are slow to reproduce, their populations may take centuries to recover, if they recover at all. This fragility underscores the dependence of the largest habitat on Earth on processes occurring in its thin, sunlit skin. So what feeds life in the dark? The answer, as far as we know, is this continuous fall of fragile transient particles, a snow that never melts, drifting forever downward. It is the simplest of processes, born from decay, yet it sustains entire worlds. And the haunting question is whether it will continue unbroken in the future. As our planet changes, will the deep still receive its rain of nourishment, or will the snow grow thin, leaving the underworld barren? What if life could feed on a rock and fire instead of sunlight? For centuries the assumption was that all living things on Earth depended directly or indirectly on energy from the sun. Plants and algae captured light, animals consumed plants or each other, and even the deep ocean seemed sustained by scraps that filtered down from above. It seemed a law of nature that light was life. Then, in the late 1970s, scientists stumbled across something that rewrote that law. In one of the most extreme environments imaginable, amid volcanic vents on the seafloor, they found entire communities of animals thriving without a trace of sunlight. The discovery of hydrothermal vents was not just a new page in biology, it was an entirely new book. The story begins in the year 1977, during a research expedition to the Galapagos Rift in the eastern Pacific. Oceanographers aboard the research vessel Nor had sent the submersible Alvin down to study spreading centres along the mid-ocean ridge. They expected barren landscapes, perhaps a few hardy microbes. Instead, they were met with chimneys billowing black smoke, towering structures of minerals that rose like factories from the seafloor. Around them, to their astonishment, were dense clusters of giant tube worms, clams, and crabs. In the pitch darkness, life was thriving in abundance that rivaled coral reefs. No one had predicted it. These vents formed where seawater percolated down through cracks in the ocean crust, was superheated by magma and then forced back up, carrying dissolved metals and sulfides. When the hot, mineral-laden water gushed back into the cold ocean, it precipitated into clouds of particles forming black smokers. Some vents emitted clear or white plumes depending on the mineral mix, but the principle was the same: water heated to hundreds of degrees Celsius, rich in chemicals seeping into a world that had never known light. The key to this hidden ecosystem was not sunlight, but chemosynthesis. Bacteria living within the vent fluids used the energy in chemical bonds, particularly hydrogen sulfide, to build organic matter. Just as plants on land use chlorophyll to trap photons, these microbes used enzymes to tap into the energy of sulfur compounds. They were primary producers, creating food from a rock and chemistry, and around them entire food webs flourished. The most iconic of these vent inhabitants were the giant tube worms, Riftia pachyptila, growing up to 2 meters long and forming dense colonies. They had no mouths, no stomachs, and no digestive systems. Instead, they housed symbiotic bacteria inside a specialized organ called a trophosome. The bacteria did the work of converting sulfides into organic molecules, and in return the worms supplied them with raw materials by absorbing hydrogen, sulfide, oxygen, and carbon dioxide from the surrounding water through their bright red plumes. The partnership was so intimate that the worms could not survive without their microbes, nor the microbes without their hosts. Alongside the worms lived other creatures equally adapted to the vent world. Giant clams and mussels housed chemosynthetic bacteria in their gills. White crabs scuttled over the chimneys, scraping up bacterial mats. Ghostly shrimp with light-sensitive patches on their backs swarmed around vents on the mid-Atlantic ridge, perhaps using faint infrared emissions from the hot water to navigate. Each species was part of a community structured around a food source that had no connection to the sun. The chemistry of vents is extreme. Fluids can reach temperatures above 370 degrees Celsius, though they cool quickly when mixed with seawater. Pressures are immense, yet animals flourish within centimetres of boiling water. Sulfides that would be toxic to most life are essential here. The animals have evolved hemoglobins and enzymes resistant to heat and metals, specialised adaptations that seem almost alien. It was a reminder that life is not fragile but astonishingly flexible. The discovery had implications beyond marine biology. If ecosystems could thrive without sunlight, powered only by chemistry, then perhaps similar systems could exist elsewhere in the universe, beneath the ice of Europa or Enceladus, or in subsurface oceans of other worlds. Hydrothermal vents became more than a curiosity. They became analogues for extraterrestrial habitability. Some scientists even speculated that life on Earth itself might have originated at vents, where mineral-rich environments provided natural reactors for organic chemistry billions of years ago. In the decades since the first discovery, expeditions have found hydrothermal vents scattered along ridges and back-arc basins around the world. Each vent field hosts its own particular community, shaped by geography and chemistry. In the Pacific, giant tube worms dominate. In the Atlantic, shrimp swarm. In the Indian Ocean, fields of mussels thrive. Despite the differences, the common thread is the reliance on chemosynthetic microbes as the base of the food web. Among the most memorable of vent inhabitants are the so-called Yeti crabs, first described in the early 2000s from vents near Easter Island. Covered in silky blonde setae that resemble fur, these crabs cultivate bacteria on their own bodies, waving their hairy claws over vent fluids to feed their symbionts. They then scrape the microbes off and eat them. The sight of crabs farming bacteria on their arms in the lightless deep is both comical and profound, a reminder of how creative evolution can be. Studying these ecosystems requires technology as ingenious as the animals themselves. Submersibles like Alvin or remotely operated vehicles are equipped with robotic arms and high-resolution cameras, capable of sampling fragile organisms and vent fluids at extreme depths. Instruments must withstand crushing pressures and searing temperatures, yet each dive reveals new species, new adaptations, and new perspectives on what life can be. To date, hundreds of vent-associated species have been catalogued, and more are discovered almost every expedition. The vents are not permanent. Chimneys collapse, flows shift, and eventually the activity wanes as heat sources migrate. Communities that flourish for decades may suddenly decline when the chemistry changes. Life at vents is therefore dynamic, colonizing, flourishing, and vanishing in cycles tied to the restless geology of the seafloor. For biologists, this raises questions about how organisms disperse between isolated vent fields, separated by thousands of kilometers of dark ocean. Larval stages drifting in currents seem to be part of the answer, but much remains uncertain. Hydrothermal vents also highlight the intersection of biology and geology. The minerals precipitating from vent fluids form deposits rich in copper, zinc, gold, and other valuable metals. These deposits have attracted interest from mining companies, and some experimental projects are already underway. Scientists caution that disturbing vent ecosystems could destroy unique life forms before they are even documented. The debate over how to balance resource extraction with conservation is ongoing, and it forces us to consider what value we assign to ecosystems we may never see firsthand. For those who study the deep, vents remain an endless source of fascination. The contrast between the apparent hostility of the environment and the exuberance of the life it supports is striking. It challenges our assumptions about habitability and forces us to redefine what we mean by a livable environment. In a sense, the discovery of vents liberated biology from the tyranny of sunlight. It showed that life could write its own rules, using chemistry as ink. What if life could feed on rock and fire instead of sunlight? We now know that it can. Hydrothermal vents are oases in the dark, places where geology and biology intertwine to create ecosystems utterly unlike those at the surface. They remind us that we have only begun to map the possibilities of life on Earth, and that the deep ocean still holds secrets as radical as any science fiction. The haunting question, of course, is how many such oases remain undiscovered, hidden in the abyss, waiting for the next submersible to stumble across them. If the surface rages with hurricanes, what does the abyss feel? The answer, for much of human history, was assumed to be nothing. Sailors and natural philosophers of earlier centuries looked at the violence of waves, the battering of winds and the chaos of storms, and imagined that all of this fury must churn the ocean through and through. Yet as science began to measure more carefully, it became clear that the deep ocean has its own rules. The gales and tempests that rip across the sea surface lose their strength rapidly as one descends, and by the time you have gone several kilometres below, the abyss is remarkably quiet. The seabed is often compared to a desert plain, not because of dryness, but because of the stillness, a place so far from the roaring interface with the air that it barely notices the weather above. To call it calm is almost an understatement. This calmness is more than just an absence of storms. It is the defining character of the abyssal environment. The waters that fill the depths between roughly 3,000 and 6,000 metres are cold, stable, and dark. They are formed far from the tropics, in the polar regions where surface waters grow dense enough to sink, carrying with them the imprint of the atmosphere they once touched. In the Southern Ocean, around Antarctica, sea ice forms in winter, and the brine rejected during freezing makes surrounding waters so salty and heavy that they plunge downward, beginning a slow crawl along the seafloor. This Antarctic bottom water, along with contributions from the North Atlantic, seeps across basins and beneath ridges, sometimes taking centuries to flow from one hemisphere to another. The abyss is therefore not only calm but ancient, filled with waters that have travelled across the globe in silence. If you were to measure temperature and salinity in this deep realm, you would find them astonishingly uniform. Surface waters differ dramatically, warmed in the tropics, freshened by rain or river mouths, and shifted constantly by winds. In contrast, the abyss sits almost unmoved. Salinity lingers within a narrow band of 34.5 to 35 parts per thousand. Temperatures hover between freezing and 4 degrees Celsius. These values change little from year to year or even century to century. It is this stability that scientists use to define the abyssal zone, marking its upper boundary not so much by depth as by the depth at which temperatures reach around 4 degrees Celsius. Depending on where you are on Earth, that may be closer to 1,000 metres, or closer to 3,000, but below that threshold you're in the abyss. The pressure, of course, is enormous. With every 10 metres descended, another atmosphere of pressure presses in. By the abyssal depths, the weight of hundreds of atmospheres has accumulated. Yet here again, calmness is the rule. Animals that live in the abyss are pressurised from within, so they do not feel the crushing force the way a human diver or a submarine might. The water is so heavy and constant that it becomes invisible to those adapted to it. Pressure is not a storm here. It is simply the background of existence. If you were to scoop up some of the mud that carpets the abyssal plains, you would find another reflection of this stillness. The sediments are fine, smooth, and layered gently. They are not churned by waves or tides the way coastal sands are. Instead, they accumulate grain by grain from the slow rain of particles drifting down from above. Much of this is biological debris, the remnants of phytoplankton and zooplankton that lived and died near the surface. Some is mineral dust blown from continents, volcanic ash, or tiny fragments of rock carried by icebergs long ago. At depths shallower than 4,000 metres, in equatorial and temperate oceans, the dominant material is often calcareous. The shells of foraminifera and coccolithophores, organisms that build with calcium carbonate. But below 4,000 metres, calcium carbonate begins to dissolve, and the composition shifts. Clay minerals and siliceous skeletons of diatoms and radiolarians take over, forming brown clays and siliceous oozes. Layer upon layer, these sediments build a record of Earth's history, a quiet archive written in mud. It is no accident that paleoceanographers turn to abyssal cores to reconstruct past climates. The lack of disturbance means the layers preserve tiny fossils, isotopic ratios, and chemical signals in chronological order. From them we have learned of ice ages, of oscillations in Earth's orbit, and of how carbon dioxide has waxed and waned in the atmosphere over hundreds of thousands of years. Without the abyssal calm, our window into past climates would be smudged and incomplete. Instead, the silence of the abyss has kept this record legible, a geological diary buried beneath kilometres of water. Nutrient salts are another reflection of the abyss's role in the planetary system. Nitrogen, phosphorus, and silica concentrations are higher here than in the surface waters. The reason is simple. In the surface, photosynthetic organisms consume nutrients quickly. In the abyss, no photosynthesis occurs, and the decomposition of organic matter raining down adds more salts. The abyss is thus a reservoir of nutrients. When circulation eventually brings some of these deep waters back to the surface, in places like the equatorial Pacific or off the coasts of Peru and Namibia, they fertilize blooms of plankton. The productivity that feeds fisheries and food webs begins in part with nutrients stored silently for centuries in the abyss. The calm waters below are linked invisibly to the bustle of life above. Oxygen tells a similar story. Abyssal waters inherit their oxygen when they first sink at the poles. No new oxygen is added once they are cut off from the surface, but their consumption is minimal. With so few animals per unit volume, the oxygen can last centuries. Even so, just above the sediments the levels may drop to near zero, as microbial activity in the mud consumes what little diffuses down. For this reason, many abyssal animals are elevated on stalks or have long legs, lifting themselves just above the most depleted layer. The calmness here is not absolute. It has gradients and dangers. But it is still far more stable than the fluctuating conditions nearer the sunlit surface, and yet even in this realm of quiet, there are motions. The abyss is not perfectly still. Oceanographers have discovered that eddies and currents twist and swirl even at great depths. The energy from storms at the surface can ripple downward, creating internal waves that propagate along density boundaries within the ocean. Over long timescales, these waves can mix water masses and sculpt sediments. Expeditions using acoustic instruments have revealed that even abyssal plains may bear ripple marks, tiny undulations that betray the passage of currents. The calm is therefore relative. Compared to the storm-tossed surface, it is tranquil, but compared to absolute stillness, it still has a pulse. Modern technology has given us tools to measure these hidden flows. Current meters anchored to the seafloor record velocities, often just a few centimeters per second, but over years they add up to significant transport. Drifting floats, tracked acoustically, have traced paths across basins. Acoustic tomography has mapped temperature and flow across entire oceans. These techniques reveal that the abyss is a critical part of Earth's climate engine. The slow, overturning circulation, moving heat and salt across hemispheres, regulates long-term climate stability. Without the abyssal conveyor, surface temperatures would be more extreme, ice ages more severe, and tropical rains less predictable. The calm waters beneath storms are, paradoxically, the great moderators of the surface climate. One of the haunting aspects of abyssal calm is its vulnerability. Because conditions change so slowly, disturbances may last far longer than at the surface. A storm's impact is gone in days. An oil spill or chemical deposit in the abyss could linger for centuries. Sediments accumulate at mere centimeters per 1,000 years, so any contamination becomes part of the geological record for unimaginable spans of time. The abyss is therefore both resilient, in its ability to remain stable for millennia, and fragile, in its inability to recover quickly from human impact. So what does the abyss feel when a hurricane spins above? Almost nothing. The waves and winds that seem so overwhelming to us are skin-deep in the ocean's body. Below a few hundred meters, their energy fades, and at thousands of meters it vanishes entirely. The calm of the abyss is not disturbed by storms, but shaped by processes on far longer timescales. The sinking of polar brines, the slow settling of particles, the geologic breathing of Earth itself. If the surface is the heartbeat of the ocean, fast and irregular, then the abyss is its deep breath, steady and almost imperceptible. If the surface rages with hurricanes, what does the abyss feel? Perhaps the more interesting question is whether the abyss notices us. For now, its calm continues, layered with sediments and carrying nutrients silently across the globe. But as we change the climate and alter the chemistry of the seas, the abyss may one day feel disturbances greater than any storm. The haunting thought is that we might awaken a realm that has been quiet for millions of years, and once stirred, its responses will last not for days or decades, but for geological ages. What unseen rivers connect the poles to the equator? To stand on the deck of a ship and look at the sea is to imagine vastness without motion, an endless surface of blue stretching in all directions. The waves may crash, the winds may stir, yet beyond the immediate drama it feels static, unmoved. But beneath this apparent stillness, the ocean carries within it a planetary-scale circulation that dwarfs any river on land. These rivers are invisible not because they do not exist, but because they flow in darkness. thousands of meters below the waves, unseen and nearly unfelt by the creatures on the surface. Their source lies at the frozen margins of the Earth, in the polar seas, where water is made heavy enough to sink. At the poles, winter transforms the ocean. As sea ice forms, it rejects salt, producing brine that is both saltier and colder than the surrounding water. In the Southern Ocean, especially near Antarctica, this brine sinks with immense weight, beginning a journey that may last centuries. The water that descends in this way becomes Antarctic bottom water, the densest water mass on the planet. Slowly, it creeps along the seabed, spreading outward beneath the Atlantic, Indian and Pacific basins, carrying with it the chemical fingerprint of its birthplace. Its rival in the Northern Hemisphere, formed in the Nordic and Labrador seas, is North Atlantic deep water, equally important but slightly less dense. Together, these masses are the great feeders of the abyssal circulation. They are not rivers we can stand beside, but they are rivers all the same, coursing around continents, spilling across ridges, and mingling in valleys thousands of meters deep. To trace them is to uncover one of Earth's hidden engines. Scientists often call this system the thermohaline circulation, from the Greek words for heat and salt. Heat and salt control density, and density drives motion. Warm, fresh water floats, cold, salty water sinks. When that water sinks, it does not vanish. It spreads, pressed outward by its own weight, hugging the seafloor, seeking equilibrium across basins. Its movement is staggeringly slow. While a river like the Amazon may cross its basin in weeks, the journey of Antarctic bottom water across the Pacific may take 1,000 years. Yet the scale makes up for the pace. These invisible rivers carry volumes far beyond any surface river, redistributing heat, carbon, and nutrients around the globe. The presence of these deep currents was suspected long before they could be measured. In the 19th century, the voyage of HMS Challenger revealed that the deep ocean was not a stagnant void, but a layered system. Samples collected from different depths had consistent temperatures, salinities, and chemical properties, showing that distinct water masses occupied distinct layers. Later, in the 20th century, scientists mapped these layers more precisely, discovering that the deep waters of the Atlantic bore the unmistakable mark of the Arctic and Antarctic, while those of the Pacific were older, depleted of oxygen, and enriched in nutrients, having drifted far from their polar sources. By comparing isotopes and chemical traces, researchers could estimate the age of a water parcel, not in human years but in oceanographic time, measured in centuries. These invisible rivers do not merely redistribute water, they shape climate itself. When cold, dense water sinks at the poles, it draws in surface water to replace it, setting up a conveyor that links surface winds to deep currents. The Gulf Stream, that warm ribbon of water streaming northward past the eastern United States, owes its strength in part to this pull, feeding the deep formation of North Atlantic waters. Without such a system, Europe's climate would be far harsher, and tropical seas would be warmer still. The abyss, in its silence, moderates the surface. But these rivers do more than move heat. They also carry carbon. As surface waters sink, they take with them dissolved carbon dioxide absorbed from the air. Locked away in the abyss, that carbon is sequestered for centuries. This process, sometimes called the biological pump when combined with the sinking of organic matter, is one of Earth's great regulators of atmospheric carbon dioxide. Without it, the rapid burning of fossil fuels would already have produced an even more extreme greenhouse effect. The abyss, in its invisible patience, buys us time. Yet this also means that the carbon we emit today may be carried into the deep sea, only to return hundreds of years later when these waters upwell again. The ocean is not a permanent sink, but a conveyor with delays so long that they feel geological. The uniformity of abyssal waters reflects their origin. Oxygen levels in young Antarctic waters are relatively high, inherited from contact with the air. By the time these waters reach the Pacific, centuries later, oxygen has been consumed by the slow respiration of deep organisms, leaving levels low. Nutrients show the opposite trend. Pour in phosphate and nitrate when they form, they gather more with each passing century as the rain of organic matter decomposes into the water column. Thus, nutrient-rich waters in the Pacific trace their ancestry to waters that began their journey in polar seas long before recorded history. This global contrast between young, oxygen-rich Atlantic waters and old, nutrient-laden Pacific waters is a testament to the length and endurance of these invisible rivers. Yet even as we map and model them, we remain humble before their complexity. The circulation is not a single conveyor belt, as some simplified diagrams suggest, but a tangled web of flows, eddies, and exchanges across basins and ridges. Seafloor topography diverts currents, internal waves mix them, and seasonal variations in winds adjust their strength. Recent measurements have shown that storms at the surface can send energy deep into the ocean, stirring these abyssal flows more than once thought possible. Satellite altimetry has revealed subtle bumps in sea level that betray the tug of deep currents. And still, even with modern technology, the paths of these rivers remain partly hidden. They are too slow to measure in a single expedition, too vast to capture in a single model. We know they exist, but the details continue to elude us. The haunting question is how stable they are. In Earth's past, abrupt climate shifts have been linked to changes in these invisible rivers. Ice cores and sediment records show that during the last ice age, the strength of North Atlantic deepwater formation waxed and waned, sometimes collapsing altogether. When that happened, Europe cooled dramatically, while the southern hemisphere warmed, an imbalance caused by disrupted heat transport. Such events remind us that the abyss is not just a passive reservoir, but an active participant in climate. If these rivers falter, the consequences ripple across continents. Today, as polar ice melts and surface waters freshen, scientists worry about the same risk. Fresh water is lighter than salt water, and if too much pours into the North Atlantic, the density difference that drives sinking could weaken. Already, instruments moored across the Atlantic have measured fluctuations in the strength of deep currents. Models suggest that a significant slowdown is possible within this century. If so, the climate consequences would be profound, altering rainfall patterns, shifting monsoons, and raising sea levels unevenly across coasts. The invisible rivers that once seemed eternal now appear vulnerable to human influence. And so, we return to the question, what unseen rivers connect the poles to the equator? They are the thermohaline circulation, the abyssal flows of cold, dense water that slip silently beneath storms and continents, shaping climate and storing carbon, connecting Arctic brines to equatorial upwelling. They are rivers without banks, without floods, without noise. They move on timescales that mock human impatience, and yet they are fragile enough to change within our lifetimes. To glimpse them is to feel both awe and unease. They remind us that Earth's greatest rivers are not those we can sail upon, but those that pass unseen beneath us, carrying the memory of ice into the heart of the tropics. Why do deep-sea creatures grow so huge? It is a question that haunts both science and imagination. We look at the pale amphipods collected from trenches, the great squids that wash ashore, the isopods the size of puppies crawling across the abyssal plains, and we cannot help but see exaggeration, as though the ocean floor is a world of distortion. It is a phenomenon called deep-sea gigantism, and while scientists have offered explanations, the truth is still uncertain. Yet the patterns are consistent enough to suggest that something fundamental in the conditions of the deep favours bodies that stretch the imagination. One starting point is temperature. The deep ocean is cold, rarely warmer than 4 degrees Celsius and often hovering closer to freezing. Cold slows metabolism. In this chilled world, organisms burn energy at a fraction of the rate of their shallow water relatives. A slow metabolism may extend lifespan, and long lives mean more time to grow. Over decades, or perhaps even a century, an amphipod may continue to add millimetres until it reaches several inches in length, far outstripping its coastal kin. The same may hold for isopods, crustaceans that in shallow waters grow to the size of a thumb, but on the seafloor can reach half a metre. Another factor is pressure. At thousands of metres beneath the surface, pressures reach hundreds of atmospheres. For vertebrates, this can be a constraint, crushing airspaces and limiting physiology. But for invertebrates with flexible bodies and fluid-filled cavities, the immense pressure may instead stabilise enzymes and cell structures that otherwise would not function. Some researchers suggest that larger bodies, with their lower surface-to-volume ratios, are better suited to withstand these conditions, reducing the metabolic cost of living under crushing weight. Pressure is not just a challenge, it may also shape the form of survival. Scarcity is another clue. Food is rare in the deep. Outside of hydrothermal vents and seeps, most life is fueled by the slow drizzle of organic detritus falling from above, the marine snow already described. In this environment, energy efficiency is everything. Larger bodies can be more efficient than smaller ones, capable of travelling farther on the same caloric intake, capable of storing more energy when food is abundant, and less vulnerable to starvation when food is scarce. Gigantic amphipods, for instance, may glide across the seafloor with less relative expenditure than swarms of tiny ones. The giants do not outcompete the small ones everywhere, but where food falls in episodic bursts, large size is an advantage. Predation also plays its role. In the deep sea, predators are fewer, the density of life is low, and the hunting strategies that work in shallow reefs do not always apply in the dark. Here, growing large may be less risky. In shallow waters, a large body is more visible, more conspicuous to predators, but in the abyssal dark, size does not betray you in the same way. The amphipod that grows 10 times larger is not more likely to be seen, and once full grown, it may be safer than a swarm of tiny bodies, each vulnerable to the first passing fish. The absence of visual predators in much of the deep ocean removes one constraint that on land and in the shallows keeps bodies smaller. The examples are striking. Amphipods collected from the Mariana Trench have been recorded at more than 10 centimetres, dwarfing their surface relatives. Isopods, sometimes called giant pill bugs, patrol the seafloor at half a metre long, scavenging carcasses with methodical patience. The giant squid, Architeuthis, and its relative the colossal squid, Mesonicoteuthis, both exemplify the extreme. Their tentacles stretch metres beyond their mantles, their eyes the size of dinner plates, evolved to capture the rare flicker of bioluminescence in the dark. Even the simple worms of the abyss reach lengths that, compared to similar species in the shallows, seem excessive. Again and again, the deep sea produces bodies that strain the definition of proportion. But gigantism is not universal. The deep ocean is also home to creatures of remarkable smallness, translucent plankton and fragile larvae that survive at scales almost invisible. The contrast suggests that size is a flexible adaptation, one path among many, not a fixed rule. Some scientists caution that our understanding is biased by what we can capture and measure. Large bodies are easier to preserve, more likely to survive trawl nets or pressure changes. Small and fragile forms may elude us, leaving an impression that giants dominate when in fact they share the abyss with multitudes of tiny forms. The deep sea resists generalization. Even so, the patterns persist across phyla, from crustaceans to cephalopods, and demand explanation. Some have proposed the temperature size rule, observed in other ecosystems, where colder environments favour larger bodies. Others emphasise the role of oxygen, noting that larger bodies require efficient oxygen use, and that cold waters, saturated with oxygen, may make this possible. Still others highlight evolutionary time. The deep ocean is stable, without seasons or storms, a world where slow growth is not punished, and lineages have had millions of years to stretch themselves into monstrous forms. The truth may be a combination. Cold slows metabolism, pressure stabilizes enzymes, food scarcity favors efficiency, oxygen availability allows growth, and low predation removes constraints. Together, they form a suite of conditions where gigantism is not inevitable but possible, a recurring outcome of survival in the deep. The phenomenon also has consequences beyond curiosity. Gigantism changes the dynamics of ecosystems. Large amphipods and isopods can consume carcasses rapidly, recycling nutrients that would otherwise linger. Giant squids become prey for whales, sustaining predators of immense size. The balance of deep-sea food webs is shaped by these giants, who act not as exceptions but as functional players in their communities. Without them, energy transfer would be slower, less efficient, perhaps incapable of sustaining the other giants of the deep. It is humbling to admit how much we still do not know. Most giant species are known only from a handful of specimens, many collected dead or damaged. Observations of live behaviour are rare, sometimes limited to fleeting glimpses on submersible cameras. The abyss swallows evidence, and our understanding remains fragmentary. Are these giants common or rare? Do they live solitary lives or gather in numbers? Do they endure for decades or only a handful of years? We have hints but no certainty. What we do know is that gigantism recurs often enough to suggest a rule, even if the rule is still blurred. From the amphipods of trenches to the squids of midwater, from isopods to worms, the pattern is undeniable. It is a reminder that life responds to conditions in ways that defy shallow expectations. To live in the deep is to adapt, and sometimes adaptation stretches bodies into sizes that to us seem monstrous. So why do deep-sea creatures grow so huge? The answer is not singular. It is a mosaic of pressures, temperatures, scarcities, and opportunities, stitched together over evolutionary time. The giants of the deep are not accidents, nor are they myths. They are the logical outcomes of survival in an environment where the rules are different, where slow is fast, where dark is safety, where vastness allows excess. They are not monsters in the sense of horror, but in the sense of marvels, creatures that remind us that our planet is stranger than we imagine. And yet, the haunting question remains. If gigantism is an adaptation we can explain, does it mean we have accounted for all of it? Or do there remain giants in the abyss that we have not yet seen, forms larger and stranger than any specimen washed ashore? The deep sea has a way of humbling confidence, reminding us that every answer is provisional, every theory partial. Perhaps the age of the monsters is not behind us, but still unfolding in the blackness below. What is the truth behind the legendary giant squid? For centuries, sailors told stories of immense arms rising from the ocean, pulling vessels into the abyss. These tales, embroidered by fear and retelling, seeded myths of sea monsters that haunted literature and art. But separating myth from biology has always been difficult when the creature itself refuses to be seen alive. The giant squid, Architeuthis, is real, though only in the last century and a half have scientists begun to assemble a picture that replaces speculation with anatomy, measurement, and rare observation. And even now, for all that we think we know, most of what we understand comes not from watching them live, but from their remains, found washed ashore, pulled accidentally in nets, or in the stomachs of the whales that prey upon them. One of the first serious breakthroughs came in the 19th century, when dead squids began appearing in coastal waters. Fishermen brought in tangled masses of arms and tentacles that seemed too large to be real. Naturalists took note, and for the first time, careful illustrations and descriptions transformed a myth into a specimen. In the 1870s, the Reverend Moses Harvey of Newfoundland purchased such a specimen and draped it across his bathtub for photography, producing the first visual record of the giant squid that was not drawn from imagination. From there, scientific descriptions followed, with Professor A.E. Verrill at Yale offering some of the first formal taxonomic work. The sea monster was not a monster, but an invertebrate of extraordinary proportions. Anatomy reveals how extraordinary it is. Like other squids, Architeuthis has a mantle containing its organs, a funnel for jet propulsion, 8 arms lined with suckers, and 2 long feeding tentacles. But everything is magnified. The feeding tentacles can shoot out many meters beyond the body, tipped with suction cups lined with sharp chitinous teeth. These are not smooth discs, but gripping tools, capable of embedding rings into the flesh of whatever they seize. The arms pull prey toward a beak as sharp as a parrot's, slicing flesh into pieces, which are then ground further by a radula, a rasping tongue lined with rows of tiny teeth. This feeding apparatus is powerful enough to handle fish and other squids, and there is evidence from beak remains in whale stomachs that giant squids sometimes even prey on one another. Its eyes are equally astonishing. Measuring up to 30 centimeters across, they are the largest eyes in the animal kingdom, the size of dinner plates. Such eyes are not merely extravagant. In the blackness of the bathypelagic zone, vision requires every photon. These huge lenses can gather faint glimmers of bioluminescence from many meters away, perhaps allowing the squid to detect the silhouette of an approaching predator, such as a sperm whale, by the way it blocks the background flickers of plankton light. To survive in near-total darkness, the squid invests in organs of perception as much as in organs of attack. Still, direct encounters remain rare. For decades, scientists and explorers tried to capture images of a living giant squid in its natural habitat, lowering cameras with bait into the dark waters. Many expeditions ended with nothing but blurred shapes or fragments of tentacle. It was not until the early years of the 21st century that real progress was made. In 2005, researchers Tsunemi Kubodera and Kyoichi Mori succeeded in photographing an Architeuthis alive at a depth of 900 meters near the Ogasawara Islands in the Pacific. The images showed not a drifting carcass, but a vigorous predator, lunging with its tentacles to seize bait. The severed limb that it left behind when it escaped confirmed its identity. This was the first clear evidence that the giant squid was not the sluggish scavenger some had supposed, but an active hunter, capable of sudden, coordinated strikes. 7 years later, in 2012, an expedition from Japan's National Science Museum, working with NHK and the Discovery Channel, filmed a giant squid in its environment for the first time. Using sensitive cameras and lights designed to mimic bioluminescent prey, they recorded a living Architeuthis several meters long, golden in colour, rising from the darkness to attack. The footage stunned viewers around the world, transforming what had been the stuff of maritime legend into a vivid, undeniable reality. It was not a monster, but a cephalopod, moving with purpose and speed, alive in a world almost no human had seen. Scientists such as Dr. Clyde Roper of the Smithsonian Institution devoted entire careers to studying these animals, often without ever seeing one alive. Roper examined specimens preserved in jars, dissected giant carcasses brought to museums, and traced their distribution across the world's oceans. His work showed that Architeuthis is not confined to one ocean, or one region, but has a global presence, appearing from New Zealand to Spain, from Africa to North America. Yet it is absent in the warmest tropical waters and the coldest polar seas, suggesting a preference for the temperate slopes of continental shelves and islands. Roper also underscored the remarkable challenge of studying them, describing the frustration of following sperm whales with cameras to their hunting grounds, only to be denied even a glimpse of the prey that leaves scars across the whales' heads. Those scars may be the most dramatic evidence of the squid's life. Circular sucker marks, each several centimetres across, cover the skins of sperm whales that strand on beaches. These scars tell of titanic struggles far below the surface, battles where giant squid lash out with their arms and tentacles against the jaws of whales weighing tens of tons. The whales, more often than not, prevail, and their stomachs are filled with squid beaks. But the fact that whales bear the scars at all tells us that Architeuthis does not go down without a fight. These are confrontations unseen by human eyes, but written on the bodies of the survivors. The size of giant squid is another subject of fascination and uncertainty. Reports of squids 60 feet long have circulated for centuries, but modern science is cautious. Because tentacles can stretch and tear, total length measurements are unreliable. The most consistent metric is mantle length, which in Architeuthis rarely exceeds 2.5 meters. With tentacles, total length may reach 13 meters, perhaps more, but evidence for individuals longer than that is tenuous. Even so, at these dimensions, the giant squid is among the largest invertebrates on Earth, rivaled only by its close relative, the colossal squid, which we will not explore here. What role does Architeuthis play in the ecosystem? It appears to be both predator and prey, feeding on deep-water fish and smaller squids, while itself forming a major portion of the diet of sperm whales. Its life cycle remains mysterious. Like other squids, it likely grows quickly, reaching maturity in only a few years, and reproduces once before dying. Females release millions of eggs, and juveniles drift in the plankton before sinking to deeper waters as they grow. But almost no one has seen the young stages in the wild, and their development remains largely speculative. It is one of many reminders that even with centuries of curiosity, the giant squid remains more unknown than known. Culturally, Architeuthis has always been larger than life. From the kraken of Scandinavian lore to Jules Verne's 20,000 Leagues Beneath the Sea, the idea of immense tentacled monsters has gripped the imagination. Yet modern science shows that the truth, while less supernatural, is no less astonishing. This is a creature with the largest eyes on the planet, tentacles long enough to strike from 10 meters away, and a body that thrives in places we can barely reach. It is not a monster, but a neighbour in the great web of life, adapted perfectly to a realm that for us is hostile and unreachable. The haunting question is not whether giant squid exist, for that is now beyond doubt, but how much of their lives remain invisible to us. We still do not know how often they encounter whales, how far they migrate, how they mate in the dark, or what their full range of behaviours might be. We have fragments, carcasses, scars, and a few fleeting images, but the complete story of Architeuthis is still hidden in the abyss. Perhaps the greatest sea monster of all is not the squid itself, but our ignorance, the vastness of what we cannot yet see. Is there something even larger than the giant squid? For a long time, Architeuthis held the crown in the imagination of science and seafaring folklore. The giant with the greatest eyes, the longest tentacles, the most fearsome reach. Yet in the coldest waters on Earth, far south of most human activity, another squid waits that may outmatch it in bulk. This is Megasharks hamiltoni, the colossal squid, a creature first suspected from fragments and whale stomach contents, and later confirmed as a body far more massive than the giant squid we already found overwhelming. It is not longer in tentacle length, but thicker, heavier, and built with a very different predatory strategy. If Architeuthis is the whip, Megasharks is the hammer. The first hints of its existence came not from nets, but from predators. For as long as humans have examined sperm whales stranded on beaches, or taken in whaling expeditions, strange squid beaks have been discovered in their stomachs. Some of these beaks were larger than any that could be matched to Architeuthis, leading zoologists to suspect a different, bulkier species living in the Southern Ocean. By the middle of the 20th century, enough of these beaks had been catalogued that scientists realised they were dealing with something distinct. A squid whose beak size implied a mantle longer than 2 metres and a total body mass much heavier than its northern relative. The Southern Ocean is a fitting habitat for such a giant. Circled by the Antarctic circumpolar current, these waters are some of the most productive on Earth, filled with krill and deep-dwelling fish that provide food for whales, penguins and squid alike. The colossal squid is rarely caught because humans seldom fish at the depths it prefers, but on the few occasions when trawlers have brought one up, the scale has been staggering. In 2007, a specimen weighing nearly 500 kilograms was hauled accidentally by a New Zealand vessel in the Ross Sea. At over 4 metres in length, with massive tentacles still intact, it was the largest invertebrate ever recovered whole. Preserved today in Te Papa, the National Museum of New Zealand, it remains the most complete view we have of this elusive species. Anatomically, Megasharks differs from Architeuthis in important ways. While both have 8 arms and 2 feeding tentacles, the colossal squid's tentacles are shorter and thicker, built less for striking at distance and more for grasping tightly. The suckers are lined not just with teeth, but with rotating hooks, making its grip even more difficult to escape. Its mantle is broader and heavier, suggesting a strategy not of speed but of ambush. Its eyes, while still enormous, appear slightly smaller in proportion than those of Architeuthis, though still rivaling any other creature in the animal kingdom. Most telling of all is its beak, which is the largest of any squid known. Beak size is often used by biologists as a proxy for overall body size, because the beak is one of the few hard parts that resist digestion. The colossal squid's beak dwarfs that of the giant squid, implying that some individuals may exceed even the large specimen in Te Papa by significant margins. Some estimates suggest maximum weights could approach 700 kilograms. Where the giant squid seems adapted to long-range attacks, the colossal squid seems designed for a different kind of hunting. Its hooks and mass suggest that rather than pursuing agile prey in open water, it may rely on surprise, ambushing large fish in the dim depths of the Antarctic seas. Some scars on the bodies of large Antarctic toothfish, an important species in those waters, appear to match the hooks of Megasharks. If true, then this squid is not simply a scavenger of drifting fish, but a direct predator of strong, muscular prey that themselves can weigh more than 100 kilograms. The physiology of Megasharks is also tied to its icy environment. The waters around Antarctica rarely rise above freezing, hovering near 0 degrees Celsius, and any creature living here must have enzymes and metabolic pathways adapted to such temperatures. A slower metabolism may explain the colossal squid's bulk, allowing it to store energy in a way that sustains long intervals between successful hunts. It is possible that the larger size is not simply for predation, but for surviving the lean times that come in waters where prey is seasonal. Unlike Archaeoteuthis, which ranges across temperate oceans, the colossal squid seems confined to the Southern Ocean, and its biology may reflect a specialization for that circumpolar world. Despite a few preserved specimens, vast gaps in our knowledge remain. We do not know the full range of its depth preferences, though most specimens have been caught at depths between 1,000 and 2,000 metres. We do not know how long it lives, though like other large squids it may grow quickly and reproduce only once. We do not know how many exist, though beak counts in sperm whale stomachs suggest they are numerous enough to form a major food source. We do not know what its eggs look like, how its juveniles behave, or how often it encounters its greatest predator. The encounters with sperm whales are particularly intriguing. Just as Archaeoteuthis leaves scars on whales in the north, colossal squid leaves scars on whales in the south. Circular sucker marks have been found on the heads of sperm whales caught near Antarctica, evidence of violent struggles far beneath the waves. Considering the colossal squid's heavier arms and hooks, those battles must be intense, and yet the whales return again and again, bearing the marks of combat but filled with beaks in their stomachs. This predator-prey relationship may be one of the most dramatic on Earth, involving some of the largest animals alive today, and yet it takes place entirely out of our sight. Studying Mesonicoteuthis has forced scientists to rethink the limits of invertebrate growth. For decades, Archaeoteuthis was thought to be the largest possible squid. Its anatomy seemed stretched to the edge of what an invertebrate body could manage without bones. But the colossal squid shows that evolution found another solution. Not length, but bulk. Not whipping tentacles, but hooked arms. Not speed, but power. It represents a different path to gigantism, one that thrives in a colder, darker ocean. The haunting question is how much larger they can become. Beak measurements suggest the potential for individuals larger than any yet seen, but without live footage, it is hard to know. Are the largest colossal squid even more elusive, living at depths or in regions that we rarely visit? Or have we already glimpsed the maximum, with the specimen in Te Papa representing the practical limits of physiology in the deep cold? Until more evidence is found, we remain in the dark, peering at fragments and scars, piecing together a picture of an animal that rivals the giant squid in awe and mystery. For now, we know only this. In the Antarctic seas, beneath the ice, swims a rival to the giant squid. It is shorter but heavier, slower but more powerful, confined to a realm humans barely touch. Mesonicoteuthis is not a legend but a fact, though a fact almost as elusive as any legend. In the balance between what we have learned and what we have yet to discover, the colossal squid remains one of the deep ocean's most haunting revelations, a reminder that even when we think we know the scale of life, the sea can still surprise us. Who wins when the largest predator meets the largest invertebrate? It is a question that has stirred scientific curiosity for centuries, though the battles themselves occur in a theatre almost completely hidden from human eyes. The sperm whale, Physeter macrocephalus, is the largest of the toothed whales and the deepest diving of all great predators, capable of plunging 2 kilometres or more in search of food. Its rival is the giant squid, Archaeoteuthis, and in the Southern Ocean, its even bulkier cousin, Mesonicoteuthis. These animals are separated by body plan, lineage, and evolutionary strategy, yet they intersect in the twilight and midnight zones of the ocean, in encounters violent enough to leave scars on skin and beaks and stomachs. The ocean has many food webs, but this one is among the most dramatic, a colossus of warm blood, sonar, and teeth against a sprawling invertebrate armed with hooks and tentacles. We know of these encounters less from what we have seen directly than from what is left behind. Beached sperm whales sometimes show the unmistakable traces of combat, circular sucker scars impressed on their heads and jaws, some small, others nearly as wide as a dinner plate. These are not the marks of fish or small cephalopods, but of giants. They suggest that the whales wrestle their prey into their mouths, with the squid's arms clamped desperately onto the skin in a futile attempt to resist. The number and a layering of scars on some whales show that such battles are not rare accidents but routine encounters, repeated across an individual's life. Inside the whale's stomachs, the evidence is even clearer. Among the masses of partially digested flesh, scientists consistently find squid beaks, the indigestible chitinous jaws that survive long after the soft tissue is dissolved. These beaks provide a record of diet more reliable than any fleeting observation. In some stomachs, dozens of giant squid beaks have been counted, revealing that a single whale can consume many in the course of a hunting season. In others, beaks of colossal squid appear, testifying that the Southern Ocean offers even greater prizes. By measuring the beaks and comparing them to known specimens, researchers can estimate the size of the prey. Some beaks indicate squids larger than any caught whole by humans, confirming that whales are indeed taking down the ocean's largest invertebrates. But how do they manage it? A sperm whale is massive, sometimes weighing more than 50 tons, but mass alone does not secure a meal in pitch darkness. The whale's greatest advantage is echolocation, a biological sonar system of extraordinary refinement. Deep inside its enormous head lies the spermaceti organ, a complex structure of waxy oil and acoustic chambers that can focus and project sound pulses. These clicks travel through the water, bounce off objects, and return to the whale's sensitive inner ears. By interpreting these echoes, the whale perceives its surroundings in 3 dimensions, even when no light penetrates. Laboratory and field studies suggest that sperm whale clicks are among the loudest biological sounds on Earth, powerful enough to stun prey at close range. Some researchers suspect that the whales use this acoustic shock not just for orientation, but as a weapon, disorienting or immobilizing squid long enough to close the distance. The squid, for its part, is not defenseless. Architeuthis wields 2 long feeding tentacles lined with suckers equipped with serrated teeth, designed to seize prey at a distance and hold it fast. Its 8 shorter arms bear similar suckers, allowing it to cling with great force to whatever it can reach. The scars on sperm whales are testimony to that grip. The colossal squid carries an even more formidable arsenal, with swivelling hooks embedded in its arms. These adaptations evolved not for whales but for hunting fish and other squids, yet in the deep they become the last weapons of resistance against a predator from above. What happens in the instant of contact is something we can only reconstruct. The whale descends, clicking steadily, until the echoes resolve a moving form. The squid senses vibrations or pressure changes and reacts with a defensive strike. Tentacles shoot out, teeth and hooks clamp down. The beak snaps in desperation. The whale rams forward, mouth open, engulfing the arms and mantle. There is thrashing, there are sucker marks burned into flesh, but the end is almost always the same. The whale rises with its meal, victorious yet scarred. The squid, for all its power, is not the hunter here but the hunted. What these battles reveal is not just the drama of predator and prey, but the scale of energy transfer in the deep sea. A whale of 40 tons cannot sustain itself on small fish or drifting plankton. It needs large, calorie-rich meals. Squid fill that niche perfectly, being abundant, muscular, and present at depths few other prey can occupy. The ocean has thus locked these 2 lineages together, one mammalian and one invertebrate, in an ecological relationship as old as their coexistence. Some scientists estimate that sperm whales collectively consume more squid biomass each year than all the fish caught by the global human fishing industry. That fact alone highlights how fundamental this unseen conflict is to the balance of the ocean. Our knowledge of these encounters is shaped not only by biology, but also by technology. In the 19th century, whalers noticed the scars and beaks, but interpreted them through the lens of myth, speaking of monsters lurking in the depths. By the early 20th century, zoologists had begun cataloguing beaks systematically, realizing they belonged to species never seen alive. In the late 20th century, with advances in acoustics and deep-sea sampling, the picture sharpened. Hydrophones deployed in whale habitats have recorded the clicking dives of sperm whales and correlated them with hunting behaviour. Satellite tags have tracked dives lasting more than an hour, plunging to depths beyond 1,000 metres. Occasionally squid parts rise to the surface after a whale hunt, further confirming the encounters below. Yet for all this indirect evidence, the actual moment of combat remains unobserved. No submersible, no remotely operated vehicle, and no human diver has ever filmed a whale and a giant squid locked in battle. Our reconstructions come from scars, stomachs, and sonar traces. There is something humbling in that gap. We can describe the physics of echolocation. We can measure the beaks. We can weigh the remains, but the theatre of life and death that produces them is still hidden. It is as if nature has granted us the evidence of conflict but denied us the spectacle. What does this mean for the outcome? In terms of survival, the whales clearly dominate. Squid are abundant in their diet, and whales continue to thrive on that resource. For the squid, the whales are one of the great selective pressures shaping their evolution. Gigantism may be partly a defense against being eaten, making them too large for smaller predators and giving them strength to resist. Their enormous eyes may help them detect approaching whales by glimpsing bioluminescence stirred up in the dark. But none of these adaptations appear sufficient to make them more than occasional victors. The squid fights, but the whale feeds, and yet the scars remain. They tell us that the squid does not always go quietly. The fact that sperm whales carry marks decades after they were inflicted shows that in some battles, the squid resisted with all the strength evolution gave it. These scars are the signatures of encounters where the outcome was never easy. Perhaps some squids do escape, slipping free from a whale's jaws to sink back into the dark. Perhaps in rare cases a whale fails and another scarred giant squid drifts away. We cannot know, and maybe that uncertainty is part of what makes the story endure. The haunting question is not just who wins, but how often. Are we underestimating the squid's role in these encounters because only the successful whales reach the surface? Could the deepest battles end differently, with a whale deterred or exhausted? In a way, the truth may be less important than the reminder it offers, that the greatest struggles of life on Earth can occur far beyond our gaze. The ocean hides its walls well, and we piece them together from fragments. What we can say with confidence is that when the largest predator of the deep meets the largest invertebrate, the result is a contest of evolutionary extremes. Teeth against hooks, sonar against eyes, lungs against gills. Each battle adds another scar, another beak, another trace of energy passed from one form to another. We will probably never witness it directly, but perhaps it is enough to know that it happens, continuously, beneath the calm surface of the seas, as it has for millions of years. How did myths of sea monsters outpace the facts? The ocean has always been both a provider and a source of terror, and it is no surprise that humanity filled its unseeable depths with creatures shaped more by imagination than by observation. Long before the first specimens of giant squid reached laboratories, the sea already carried reputations of leviathans, krakens, and monks of the deep. Our eyes are poor instruments when confronted with waves, fog, and the flicker of strange carcasses washed ashore. For centuries, sailors and scholars tried to make sense of fragments and shadows, and from those fragments grew an archive of myths that linger even today. The earliest records come not from marine biology, but from medieval chronicles and sailors' tales. In the 16th century, several curious fishes were described in Denmark. These were said to have heads like men, clothed in the robes of monks, and they were called sea monks. What they really were remains uncertain. Historians suggest oversized squid, or large rays, glimpsed in distortion. But in the absence of anatomical knowledge, the impulse was to humanize them, to fit them into familiar categories of the sacred and the uncanny. A monk in the waves was easier to tell as a story than a tentacled mollusk whose body plan defied imagination. In Norway and Iceland, another legend took hold. This was the kraken, said to be so enormous it could be mistaken for an island. Sailors told of whirlpools formed when it sank beneath the surface, and forests of tentacles that could wrap around a ship's hull. These were not scientific reports but oral traditions, preserved in poems and later natural histories that mixed fact and fable. By the 18th century, writers such as Erik Pontoppidan, Bishop of Bergen, treated the kraken as a plausible creature, perhaps a giant squid or a new species of whale. He described it as the largest animal in the ocean, a menace to ships and a sign of divine wonder. The kraken entered European thought not as a curious invertebrate but as a monster of scale, and the very word kraken still carries that sense today. As natural history matured in the 19th century, the tone of these accounts shifted. The Reverend Moses Harvey in Newfoundland purchased a dead giant squid in 1873 for $10 from a fisherman who had snagged it accidentally. He draped the carcass over his bathtub, producing the first photograph of a giant squid, published in 1874. It was grisly but momentous evidence that at least some of the stories of monsters had roots in reality. Harvey's specimen was used by Yale zoologist Addison Verrill to describe Architeuthis more accurately. What had been rumour and myth was finally being pulled into the framework of taxonomy. But the human imagination did not discard the monster so easily. At nearly the same moment, literature seized upon the idea of the giant squid as a symbol of the unknown. Jules Verne's 20,000 Leagues Under the Seas, published in 1870, gave the world its most famous fictional squid. In Verne's narrative, a massive cephalopod attacks Captain Nemo's submarine Nautilus, pulling sailors into the sea with its writhing arms. The description was vivid enough to etch itself into the cultural record. A terrible creature with tentacles like serpents, eyes glaring in the dark, a mouth like a beak capable of devouring men whole. Verne's work was fiction, but it borrowed just enough from natural history to feel possible, and that blend of plausibility and terror made the monster endure. In the decades that followed, popular culture returned to the squid again and again. Illustrations in magazines exaggerated its proportions until it rivaled whales and ships. By the mid-20th century, cinema adapted these visions into moving images. The 1954 Disney film adaptation of Verne's novel created an elaborate mechanical squid for the attack sequence. The model required dozens of operators, wires, and stagecraft. Yet the spectacle convinced audiences of the possibility of such an encounter. The image of a squid wrapping its arms around a vessel became part of the shared language of sea monsters, regardless of what zoologists were publishing in journals. Other myths followed similar patterns. The sea bishop or mermen described in European chronicles were probably misidentified fish or squid, but they became illustrations in bestiaries. In the 20th century, pulp novels and films inflated the squid again, often to absurd sizes, sometimes over 100 feet long, transforming it into a metaphor for human fears, the unknown, the uncontrollable, the alien. In Peter Benchley's 1991 novel Beast, adapted for television in 1996, the giant squid returned as an antagonist, stalking humans with deliberate malice. These depictions tell us more about cultural anxieties than about molluscan anatomy. The persistence of these monsters is not surprising. For most of history, humans had no way to observe the deep ocean directly. What little evidence existed came in the form of carcasses washed ashore, pieces of tentacle cut from fishing lines or scars on whales. Each fragment left ample space for imagination to fill in the rest. Where science lacked detail, myth supplied narrative. And myths are sticky. They satisfy emotional needs that facts sometimes do not. A monster can embody awe, terror, or divine judgment, while a cephalopod with tentacles and a beak is simply another animal in the long chain of life. Yet even as the scientific record grew, the myths did not vanish. They coexisted, sometimes even in the same minds. Clyde Roper, one of the foremost experts on giant squid, has often noted how even seasoned scientists feel a thrill when confronted with the sheer scale of a specimen. The rational description and the visceral impression can live side by side. A squid may be an invertebrate mollusk, but when it stretches across a room, it still looks like a monster. The boundary between myth and fact is not a clean line, but a spectrum of human response. The question then becomes, what do these monsters say about us? Perhaps they reveal how humans have always projected our fears onto the unknown. The ocean, vast and uncharted, served as a canvas for our anxieties about what lurked beyond sight. When storms sank ships, it was easier to imagine tentacles pulling them down than to attribute it to wind and waves. When strange shapes washed ashore, it was easier to see a monk's robes or a serpent's coils than to recognize the anatomy of a cephalopod. The monsters filled the explanatory void. Even now, in an age of submersibles and high-resolution cameras, the cultural image of the kraken survives. It appears in video games, films, and advertising, often more recognizable than the real Architeuthis. The monster is marketable. The animal, with its complex but less cinematic biology, is harder to sell. This tension between science and story is not unique to the squid, but the squid exemplifies it vividly. The imagined monster was larger, hungrier, and stranger than any real specimen, but it served a purpose, to remind us that there are forces beyond our control. In the end, the monsters we imagined are less about the ocean and more about ourselves. They map the boundaries of human knowledge across centuries, marking the places where evidence thinned and imagination rushed in. They show us how fear and wonder can intertwine, how myth can outpace fact, and how even when facts catch up, the myths remain. And so the haunting question remains, when we look into the deep, do we truly see the creatures there, or do we still see the shadows of the monsters we invented? Perhaps the ocean will always be both, a realm of real animals and a mirror for our oldest fears. What tools let us see where no human can swim? For centuries, the ocean's depths were places of speculation, described through ropes, weights, and sailors' tales. But the 20th century began to change that. The deep sea slowly shifted from a realm of imagination to one that could be observed directly, not by lungs or by bravery alone, but by machines designed to endure where human bodies could not. If we are honest, every breakthrough in ocean science rests on this blunt fact. Without tools, the abyss would remain hidden. Our eyes, our bones, our air-filled lungs are simply too fragile to survive the weight of miles of water pressing down. So we have had to invent instruments that see, measure, and sometimes even stand in for us. The first half of the 20th century was dominated by daring experiments in pressure-resistant vessels. In 1930, American naturalist William Beebe and engineer Otis Barton built the bathysphere, a steel ball lowered on a cable off Bermuda. It was primitive compared to what would come later, a hollow sphere with thick walls and tiny quartz windows, but it carried Beebe and Barton deeper than any human had ever gone at that time. By 1934, they had descended to more than 900 meters. For the first time, human eyes peered directly into the twilight and midnight zones. The bathysphere could not steer, and its crew depended entirely on the surface winch, but it marked a turning point. No longer were we limited to dredges or surface nets. Direct observation had begun. The post-war decades brought even bolder designs. In 1960, the Swiss-built Trieste bathyscaphe, piloted by Jacques Picard and Don Walsh, achieved something thought impossible, a dive to the Challenger Deep in the Mariana Trench. At nearly 11,000 meters, they reached the deepest place on Earth. The vessel withstood pressures more than 1,000 times that of the surface, its steel cabin protected by a gasoline-filled float that resisted compression. They reported seeing the seafloor, sediment stirred up by their landing, and even a flatfish-like creature. Whether that animal was truly a fish or an artifact of observation has been debated, but the descent itself was history-making. For the first time, humans had physically reached the deepest trench. After Trieste, exploration became more systematic. In the 1960s, the United States Navy and later civilian institutions developed Alvin, a deep submergence research submersible. Unlike the one-off descent of Trieste, Alvin was designed for repeated dives, carrying scientists directly to depth of more than 4,000 meters. It was Alvin that enabled the discovery of hydrothermal vents in 1977, where entire ecosystems thrived without sunlight. Alvin's maneuverability, with its robotic arms and viewport domes, allowed scientists to sample rocks, measure temperatures, and bring back living organisms from places no human could otherwise reach. Alvin remains active today, modernized with upgraded systems, and has completed thousands of dives. Other vessels complemented Alvin's role. The floating instrument platform, known as FLIP, created in the 1960s, offered stability at the surface. Towed to location, it could be flooded and rotated upright so that most of its hull stood below the waves. In this vertical position, it became immune to surface swells, providing an incredibly stable platform for measuring currents, sound, and other physical properties of the sea. Though it did not dive itself, Flip showed the ingenuity required to adapt to the ocean's instability. Drilling ships brought another dimension to ocean science. The JOIDES Resolution, beginning in the 1980s, was built to sample beneath the seafloor. Outfitted with dynamic positioning systems, it could remain steady while lowering drill strings thousands of meters into the crust. Through these cores, scientists reconstructed histories of climate, plate tectonics, and ocean circulation. Unlike Alvin or Trieste, it did not explore by vision but by extracting the physical record of millions of years stored in sediments. With these samples, we learned about ice ages, carbon cycles, and the movements of continents. Meanwhile, technology began to shift toward uncrewed systems. By the late 20th century, remotely operated vehicles, or ROVs, extended human reach without human risk. Tethered to surface ships, they could descend to extreme depths, powered and guided by cables transmitting data and video. ROVs brought back high-resolution images of wrecks such as the Titanic, but also explored black smokers, trenches and habitats, where delicate creatures could be observed without the distraction of a human presence. Their cameras could linger for hours where a submersible might run out of air. Their manipulators could collect fragile corals and sediments without risking life. Autonomous underwater vehicles, or AUVs, followed. Unlike ROVs, these were untethered, programmed to survey wide areas, mapping seafloor topography with sonar, measuring temperature and salinity, and capturing images. AUVs could glide silently through the deep, covering distances impractical for tethered machines. Their development paralleled advances in computing and batteries, showing how ocean exploration is tightly linked to progress in technology beyond the sea. The Deep-Sea Challenger, built for filmmaker James Cameron, reminded the public of Trieste's achievement. In 2012, Cameron descended solo to the Challenger Deep, capturing hours of video and samples. Unlike Trieste, his submersible carried high-definition cameras and modern navigation, offering not just proof of descent but scientific data. This marked another symbolic milestone. Technology had advanced enough to make what was once a singular feat into something reproducible, if still costly and rare. Smaller tools have also played a part. Criticam, developed in the 1990s, is a small camera attached to animals such as whales and seals, offering glimpses into how they move and dive in the dark. Rather than sending humans down, these devices piggyback on creatures already adapted to pressure and cold. They return footage of dives, feeding, and even encounters with prey like squid. In this way, the animals themselves become explorers. Beyond cameras, the basics of oceanography rely on instruments that measure physical properties of the water itself. The Conductivity Temperature Depth Profiler, or CTD, is now standard. Lowered from research ships, it records salinity, temperature, and pressure with remarkable precision. These readings reveal currents, layers, and the mixing of water masses. The CTD has become the workhorse of modern ocean science. Less glamorous than a submersible but foundational to every data set. With such instruments, we can trace the formation of abyssal waters, understand climate-driven circulation, and observe changes over decades. In truth, every machine that goes down into the ocean faces challenges of pressure, cold, and isolation. Electronics must be housed in oil-filled containers to equalize pressure. Metals must resist corrosion, and power sources must last long enough to outpace the distance of recovery. Communication is limited because radio waves cannot travel far in seawater, so acoustic signals are used instead, slow and subject to distortion. Each success reflects years of engineering devoted to solving the peculiar physics of the deep, and yet, despite this ingenuity, the majority of the ocean remains unexplored. Estimates suggest we have mapped less than 1/4 of the seafloor in detail. The abyss still conceals landscapes we have never imaged, and life forms we have never recorded. Our machines have made windows, but they are still narrow windows, and we peer through them cautiously. The story of exploration is not one of triumph, but of partial glimpses. We are humble witnesses, aided by tools, still constrained by physics and resources. The haunting question is whether we will ever see the deep ocean fully. Each new machine extends our reach, but each also reveals just how vast the remaining unknown is. The ocean does not yield its secrets easily. It demands invention after invention, and still it keeps most of itself out of sight. Perhaps that is part of its role for us, to remind us that, even in the 21st century, there are places on Earth where mystery remains stronger than certainty. What did humans send even to the most solitary place on Earth? It is one thing to imagine an empty trench, 11 kilometers deep, isolated from sunlight, sound, and storm. For most of human history, we assumed such places were immune to our presence. Too far, too hostile, too remote. But when explorers lowered cameras into the Mariana Trench in the 21st century, they did not just find amphipods, snailfish, and the slow drift of organic debris. They also found plastic bags. In 2018, researchers documented a single-use plastic bag resting quietly at the bottom of the Challenger Deep, the lowest point on the planet. It was an almost absurd sight. Something made to hold groceries for a few minutes had sunk to the most inaccessible place in the world, where it may persist for centuries. The discovery was not an anomaly. Plastics and other pollutants have been recorded across the Hadal realm. We have left fingerprints even where no footprints can exist. This unsettling presence builds on decades of evidence. In the late 20th century, scientists began to measure microplastics in surface waters, small fragments from degraded packaging, fishing gear, or synthetic textiles. Over time, it became clear these particles do not stay at the surface. Carried by currents, weighed down by biofilms and debris, they sink. They accumulate in sediments thousands of meters below, mingling with natural marine snow. Samples from deep cores reveal layers of plastic fibers interspersed with shells and clays, a stratigraphy of human industry recorded in the abyss. Some studies suggest there may already be more plastic particles than plankton in certain regions of the ocean, a staggering inversion of what life in the sea was built upon. Even more troubling are the toxins that plastics and other wastes carry with them. Persistent organic pollutants, from industrial chemicals to pesticides, adhere to synthetic surfaces. When amphipods or other scavengers ingest these fragments, they accumulate chemicals that the deep sea was never meant to contain. In 2017, a study found amphipods from Mariana and Kermadec trenches carrying concentrations of industrial pollutants comparable to some of the most contaminated rivers on the surface. The very creatures that embody resilience to pressure and cold now also carry the molecular echoes of factories, landfills, and exhaust. Heavy metals and radioactive isotopes have also reached the deep. Sediment analysis shows traces of lead from gasoline, mercury from coal burning, and even plutonium isotopes from nuclear testing in the mid-20th century. These markers now serve as timestamps, artificial horizons within the otherwise slow accumulation of abyssal mud. In a way, they have become geological signals of our species, a layer geologists of the future might use to define the Anthropocene. We did not just mark the land and atmosphere. We etched ourselves into the deepest plains and trenches. Even shipwrecks and abandoned technology form part of this hidden archive. The Titanic lies nearly 4 kilometers down, its steel hull colonized by bacteria that slowly consume it. Warships, planes, and cargo vessels rest at abyssal depths, leaking metals, oils, and paints. Some act as artificial reefs, but their presence is unplanned, unstudied, and enduring. Lost fishing gear, nets, lines, and traps sinks endlessly, a phenomenon often called ghost fishing, where discarded tools continue to entangle life for decades. Some of these nets have been seen draped over corals in places no diver could ever have set them. The irony is hard to escape. We designed these materials for convenience, durability, and low cost, and in doing so we gave them lifespans far beyond our intention. A bag, a bottle, or a fragment of nylon may remain intact for hundreds of years, long outlasting the people who discarded it. In the deep ocean, where light and heat are scarce, degradation slows even further. What enters may remain almost unchanged. The trench, once imagined as a pure abyss, is now a vault of our disposables. Scientists face the difficulty of measuring this footprint accurately. Sampling the deep ocean is expensive and rare, meaning data points are sparse. Yet every time a new expedition probes a trench, plastics appear. In some cases, ROV footage shows fibers floating in the water column, drifting like artificial snow. In others, core samples bring back microplastics embedded in the ooze. Even in places far removed from industrial coastlines, the signal is clear. Currents and sinking particles distribute waste globally, bypassing the boundaries we imagine. The ocean connects everything, including our neglect. This presence alters not just chemistry, but perception. The idea that no part of Earth is untouched by human activity becomes less metaphorical when a plastic wrapper is seen in the Challenger Deep. Philosophically, it forces a reckoning. The places we once saw as wilderness are part of our system now. The trenches are not beyond our reach. They are within our impact. Whether or not we visit them often, they share in our story. The haunting question is not simply how much waste has arrived, but how it will interact with life in the centuries to come. Will deep-sea creatures evolve new tolerances, incorporating synthetic fragments into their biology as if they were shells or stones? Will sediments preserve a layered record of plastics, marking the 20th and 21st centuries as sharply as volcanic ash layers mark ancient eruptions? Or will future explorers find the trenches less as ecosystems and more as museums of discarded material, stocked with the unintended exports of a species that built convenience at the cost of permanence? We cannot know yet. The abyss gives up its answers slowly. But what is already certain is this: even the remotest place on Earth is not beyond us. We have left things behind, and they will remain long after we are gone. The ocean, vast as it is, has absorbed not only our myths and our machines, but also our waste. It carries them into darkness, where they rest as quiet reminders that no frontier is safe from our touch. What if the greatest monsters are still unseen? It is a question that has lingered over the ocean since long before science tried to illuminate it. Sailors once filled the void with stories of krakens and leviathans. Today we fill it with sonar maps, remotely operated vehicles and camera traps. But the result is the same. For all we have measured, the ocean still resists being fully known. More than 2/3 of the planet is covered in water, yet by most estimates we have directly explored perhaps 1/10 of it, and even that fraction only superficially. There are still places no probe, no diver, no camera has ever visited. The deep remains, in the truest sense of the word, undiscovered. The paradox is easy to miss. Satellites can map the surface of Mars or the Moon with exquisite detail, yet the floor of our own ocean remains blurred. Much of what we know about its topography comes not from seeing, but from inference, reading the shape of the sea surface as gravity bends water over ridges and trenches. When submersibles do descend, they illuminate only a narrow cone in the darkness, a stage no wider than a few meters. Beyond the light, there is endless black. We cannot know what might be watching from just beyond the reach of the cameras. This ignorance is not failure, but inevitability. The ocean is simply too vast. Its pressure punishes intrusion, its cold slows machinery, and its distance strains human resources. Every sample, every hour of video, is hard won. And so, we live with a patchwork of glimpses. A snailfish from one trench, a shrimp from another, a new microbe clinging to a vent. Each discovery feels monumental, but each also reminds us how little we see of the whole. The best estimates suggest millions of species await identification in the sea. Some will be tiny, some may be immense, but most will never be known in our lifetimes. There is also the question of behaviour. Even the animals we know exist are in truth strangers. A giant squid has been filmed alive only a handful of times. Sperm whales descend into darkness to hunt. But their duels with squid are inferred from scars, not observed in the act. The vertical migrations of countless fish and plankton create what is arguably the largest daily movement of biomass on the planet, and yet we have only sketched its outlines. What does it look like? A river of life rising and falling in silence across every ocean, every night. We can measure it with sonar, but we cannot yet picture it with clarity. In the future, technology may sharpen our vision. Advances in robotics, satellite sensing, and genetic sampling will expand the boundaries of what we can know. Environmental DNA, shed by organisms into the water, can reveal presence without sighting, hinting at creatures swimming nearby that evade our cameras. Autonomous drones may one day patrol trenches for months at a time, sending back continuous data instead of rare snapshots. But even if we perfect these tools, the question remains, do we want to know everything? Part of the ocean's power lies in its refusal to be fully charted. There is comfort, strange as it sounds, in ignorance. To admit we do not know what lies 11 kilometers below us is to accept humility. For a species that has paved and catalogued so much of the land, that humility may be healthy. The deep sea insists that Earth is not conquered. There are still mysteries immune to our schedules, our industries, our insistence on control. In a sense, the unknown itself has become a kind of sanctuary, a refuge for imagination and for science alike. And so we end where we began, with questions. What creatures glide unseen through the midnight waters? How many trenches hold ecosystems we have not yet brushed against with a camera? What chemical worlds churn in vents still undiscovered? we cannot answer yet. Perhaps we never will. But maybe that is the point. The deep ocean, in all its darkness and silence, reminds us that not everything must be solved to be meaningful. It is enough sometimes to know the mystery is still there, waiting.